Hello there, and welcome back to the Sleep Science. You step outside into the pale light of early 2026, and the sun looks harmless enough. Just a bright disk climbing over rooftops, warming the edges of clouds like a lazy cat stretching across the sky. It feels ordinary, comforting even, and yet somewhere between that golden glow and the silent hum of satellites orbiting above you, something is off. The star you depend on for literally everything. Heat, light. The reason your houseplants haven't filed a complaint is behaving in ways scientists didn't expect. You probably won't survive this. Not because the sun is about to explode tomorrow, relax, but because if it truly decided to misbehave on a grand scale, there's very little you, your Wi-Fi router, or your emergency stash of granola bars could do about it. Or that's the gentle cosmic reality check. So before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And as you settle in, tell me where you're listening from and what the local time is. I always love imagining this story drifting across different time zones, like sunlight itself rolling over the curve of the earth. Now dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. You tilt your head back and imagine the sun not as a flat circle, but as a roiling sphere of plasma nearly 1.4 million kilometers wide. That's about 109 Earths lined up across its diameter, an absurd scale that makes your daily to-do list feel mercifully small. At its core, one hydrogen nuclei fuse into helium under pressure so intense they make the bottom of the ocean seem like a casual spa day. Every second, the sun converts about 600 million tons of hydrogen into helium. That's a mainstream, textbook fact. It has been humming along like this for roughly 4.6 billion years, a steady nuclear engine. Except now in 2026, the hum has a wobble. Solar observatories, both on Earth and in orbit, have been quietly collecting data for decades. They track sunspots, magnetic fields, ultraviolet output, and the solar wind. Scientists expected solar cycle 25, the current 11-year cycle, to peak around this time with moderate activity. Instead, instruments are registering bursts of energy and magnetic complexity that overshoot earlier forecasts. It's as if the sun glanced at the prediction charts and said, "Ahi, cute guess." Sunspots, those darker patches caused by intense magnetic activity, are appearing in clusters more numerous and more magnetically tangled than models anticipated. Historically, we know sunspots follow a fairly reliable pattern. They increase towards solar maximum and decrease towards solar minimum. That pattern has been observed since Galileo first sketched sunspots in 1610, risking accusations of heresy just to say, hey, the sun has blemishes. But in 2026, the numbers and intensity aren't lining up neatly with projections published only a few years earlier. You imagine scientists in control rooms lit by screens, watching magnetic maps bloom in electric blues and reds. There's excitement, sure, but also a threat of unease. Because when your nearest star deviates from the script, even slightly, it matters. Here's the strange part. The sun isn't brighter in any dramatic, sunglasses melting way. Your morning still looks like morning, but subtle shifts in ultraviolet radiation and magnetic flux are rippling outward. Satellites feel it first. Increased solar activity heats Earth's upper atmosphere, causing it to expand. That expansion creates more drag on satellites in low Earth orbit. Space agencies have already performed small orbital corrections earlier than expected this cycle. It's like the atmosphere puffed out its chest unexpectedly, and the satellites went, "Oh, sorry, didn't see you there." A quirky tidbit? In the 1800s, some astronomers believed sunspots might be openings in the sun's surface, revealing a cooler interior. Essentially cosmic potholes. Imagine thinking you could peer into the sun like it was a slightly cracked lava lamp. And we've come a long way since then. Now we use helioseismology, studying vibrations on the sun's surface, to infer what's happening deep inside. And those vibrations in 2026 are adding to the intrigue, hinting that internal magnetic flows may be more turbulent than models predicted. Historians still argue whether past civilizations truly linked solar activity to earthly events or simply noticed coincidences and built myths around them. Ancient Chinese astronomers recorded unusual black spots on the sun visible to the naked eye during heavy atmospheric haze. Medieval chroniclers sometimes described red auroras as omens of war. Were those periods tied to heightened solar activity? The data is fragmentary, but the curiosity endures. Now fast forward to you, standing under a sky threaded with invisible radiation and magnetic fields. And the sun's magnetic field is in the midst of its cyclical reversal process, a normal part of the 11-year rhythm. North becomes south, south becomes north. It sounds dramatic, but it's routine. Except in 2026, the timing and asymmetry of this flip appear slightly uneven between hemispheres. Solar physicists are debating whether this asymmetry signals a stronger upcoming maximum or a more chaotic decline. And here's the gentle irony. The sun has always been dynamic. It's a giant ball of electrically charged gas, not a polite desk lamp. Expecting it to behave perfectly is like expecting your cat to respect personal boundaries. Still, modern civilization adds stakes that didn't exist in Galileo's time. Power grids, GPS, aviation routes, financial systems. They all hum along under the assumption that space weather will remain within manageable bounds. You feel a faint thrill in realizing that the sky above you is not static wallpaper. It's a living system, layered and shifting. The sunlight on your skin left the sun's surface about 8 minutes ago. Before that, it may have spent thousands of years bouncing around inside the sun's radiative zone, slowly migrating outward like a photon stuck in cosmic traffic. So when scientists say the sun is acting differently, they're not talking about a flicker you can see with your eyes. They're describing patterns emerging from oceans of data, deviations in magnetic topology, surges in high-energy emissions. 3 light jokes later, and you're still here, comfortably intact, which is reassuring. The sun isn't a villain. It's just restless. And that restlessness is measurable, trackable, slightly unpredictable. As 2026 unfolds, researchers recalibrate their models in real time. They compare satellite data, cross-reference with historical cycles, and quietly ask whether this is merely an enthusiastic peak or the hint of a deeper shift in solar dynamics. You stand there a moment longer in that ordinary golden light, aware that above the blue sky, 150 million kilometers away, plasma arcs taller than Earth are twisting through magnetic fields strong enough to snap and reconnect with explosive force. It's beautiful, it's powerful, and it's behaving just differently enough to make the experts lean forward in their chairs. The star at the center of your life is reminding everyone that it is not a metronome. It is a furnace with moods. And you, so tiny and thoughtful under its glow, are about to follow those moods deeper into the story. You continue standing under that deceptively calm morning sky, and if you squint, please don't actually squint at the sun. Your retinas deserve better. You might imagine you can sense its rhythm. For centuries, astronomers have described that rhythm as an 11-year solar cycle. Activity rises, peaks, and falls with comforting regularity. Sunspots multiply, flares intensify, magnetic poles flip, and then everything quiets down again. It's the cosmic equivalent of a heartbeat, except in 2026, that heartbeat feels off-tempo. The current cycle, Solar Cycle 25, officially began in December 2019, when the previous minimum bottomed out. Early forecasts from NOAA and NASA predicted a relatively mild cycle, similar to the subdued Solar Cycle 24 before it. Some models even suggested we were entering a long-term period of weakening solar activity. Scientists felt reasonably confident. The sun had been trending slightly quieter over the past few decades. Nothing alarming, nothing cinematic. But by 2023 and 2024, sunspot counts were climbing faster than predicted. By 2025, the numbers were already rivaling stronger cycles from the late 20th century. And now in 2026, instead of tapering neatly toward a peak and gentle decline, activity is surging in bursts that overshoot earlier projections. It's not chaos, but it's not following the script either. You imagine a wall of graphs in a research lab, smooth curves sketched years ago in careful anticipation. Now the real data points poke above those curves like rebellious teenagers ignoring curfew. Not wildly, not just enough to make everyone shift in their seats. The 11-year cycle itself is rooted in the sun's magnetic dynamo. Deep inside, hot plasma churns and rotates at different speeds, faster at the equator, slower at the poles. This differential rotation twists magnetic field lines over time. Eventually, they tangle, snap, and reorganize, driving sunspots and flares. The cycle culminates in a magnetic pole reversal, after which the pattern resets. That much is mainstream astrophysics. But here's the catch. While the cycle averages about 11 years, it isn't perfectly regular. Some cycles last 9 years. Others stretch to 14. Their strength varies dramatically. Solar cycle 19, which peaked in 1958, was exceptionally intense, the strongest on record in the space age. By contrast, cycle 24 was relatively weak. Predicting the next cycle is notoriously difficult because the sun's interior flows are complex and only partially observable. In 2026, scientists are noticing that cycle 25's ascent didn't just exceed predictions, it did so unevenly. The northern hemisphere of the sun ramped up faster than the southern hemisphere, creating an asymmetry that wasn't fully anticipated. It's like the sun decided to lift weights with one arm first. Historians still argue whether earlier grand patterns in solar activity, like extended lulls, follow hidden long-term cycles beyond the familiar 11-year rhythm. There's evidence of a roughly 80 to 100-year Gleisberg cycle, a slower modulation in overall strength. Some researchers wonder if we're witnessing the upswing of such a pattern. Others caution that it may simply be statistical noise dressed up as destiny. The debate hums quietly in conference halls and journal articles. And then there's the curious twist. Even as sunspot numbers surge, certain magnetic measurements suggest irregular internal flows. Helioseismic data, those subtle oscillations rippling across the sun's surface, hint that the conveyor belt-like circulation of plasma beneath the surface may have sped up in some regions. If that flow changes speed, it can alter the timing and intensity of cycles. A quirky historical footnote: in the early 20th century, before space-based instruments, some scientists tried to correlate solar cycles with wheat prices. The idea was that solar activity influenced climate, which influenced harvests, which influenced markets. Imagine checking sunspot counts before buying bread futures. While modern climate science is far more nuanced, and it's true that solar variability can subtly influence Earth's upper atmosphere and space weather, the wheat theory, though, remains more dinner party trivia than economic strategy. As you drift through these patterns, you begin to appreciate how much modern life depends on the sun behaving within expected ranges. During stronger solar maxima, ultraviolet radiation increases, heating Earth's thermosphere. This causes it to expand, which increases drag on satellites. In fact, during heightened activity in the early 2000s, some satellites lost altitude more quickly than engineers planned. Now in 2026, satellite operators are watching closely again, recalculating orbital lifetimes as activity spikes earlier and harder than anticipated. And here's a gentle joke for you. Humanity can stream movies from space, land probes on comets, and argue online about pineapple on pizza. But predicting our own star's mood swings? Still tricky. The sun remains gloriously unimpressed with our spreadsheets. What makes this cycle particularly intriguing is not just its strength, but its shape. Instead of a smooth climb to maximum, researchers are observing multiple surges, peaks within peaks. Some scientists refer to this as a double-peaked maximum, a phenomenon seen in past cycles, but not always predictable. The magnetic complexity in certain active regions is unusually high, producing tightly wound field lines that store vast energy. Historians still argue whether past double-peak cycles were harbingers of especially volatile space weather or simply aesthetic quirks in the data. The evidence is mixed, but in 2026, with more satellites and instruments than ever before, every spike is recorded in exquisite detail. You picture the sun not as a steady drumbeat, but as a jazz musician improvising around a theme. The 11-year cycle is the melody. The improvisations, the asymmetries, the surges, the unexpected plateaus are what keep solar physicists awake at night, sipping coffee under fluorescent lights while the star itself blazes 150 million kilometers away, entirely unaware of the fuss. And yet, despite the deviations, there's no sign of imminent catastrophe. The total solar irradiance, the overall energy output, has only varied by about 0.1% across cycles in the satellite era. That's remarkably stable for a nuclear furnace. The changes we're discussing are subtle in total brightness, but profound in magnetic complexity. You let that sink in. The sun isn't brighter in a way you can feel on your skin. Instead, like its invisible architecture, its magnetic skeleton is shifting in ways that defy neat prediction. As 2026 unfolds, the cycle continues to challenge expectations. Researchers refine their dynamo models, feeding in updated flow speeds and magnetic measurements. Some quietly revise earlier forecasts. Others double-check calibration data just in case. Because when the most reliable clock in the solar system ticks slightly off beat, you don't panic. You listen more carefully. And so you keep listening, feeling the steady warmth on your face while knowing that beneath that golden surface, the rhythm of the sun is bending, stretching, and improvising in ways scientists didn't quite see coming. You drift a little closer now, not physically, of course, because that would be a very short and extremely crispy story, but in imagination. After you hover above the sun's surface, where vast continents of magnetism twist and knot themselves into dark freckles called sunspots. For centuries, sunspots have been the most visible sign that the sun is not a smooth, perfect orb. When Galileo observed them in 1610, he carefully tracked their motion and realized the sun rotates. That alone was revolutionary. Later astronomers noticed something even more intriguing. Sunspots don't appear randomly. They follow a pattern known as Spur's law, emerging at mid-latitudes early in a solar cycle and gradually migrating toward the equator as the cycle progresses. When plotted over time, they create the famous butterfly diagram, wings of activity drifting inward across the solar surface. But in 2026, those butterfly wings look slightly smudged. Sunspots are appearing at latitudes that don't quite match the expected phase of the cycle. Some clusters are lingering higher than anticipated. Others seem to surge closer to the equator earlier than models predicted. It's not a total breakdown of the pattern, but it's enough to make solar physicists lean in and zoom the graph to 400%. You imagine standing on the solar surface, again hypothetically and fireproof, watching towering magnetic loops arc overhead. A sunspot itself is cooler than its surroundings, about 3,500 to 4,500 degrees Celsius instead of the usual 5,500. Cooler, of course, is relative. It's like saying lava is less spicy than the core of a volcano. Sunspots appear dark only because they are slightly cooler than the blinding photosphere around them. In 2026, not only are sunspots more numerous than forecasted, but some are magnetically complex, classified as delta regions, where opposite magnetic polarities are packed tightly together. These regions are notorious for producing powerful flares. The frequency of such complex regions has ticked upward beyond early cycle predictions. Mainstream solar data confirms that Cycle 25's sunspot number surpassed NOAA's initial forecast range earlier than expected. That's not speculation, it's measurable. But the distribution, the geographic choreography of these spots, is adding a layer of intrigue. Historians still argue whether anomalies in sunspot latitude patterns in past centuries were early warnings of broader magnetic reorganizations or simply artifacts of limited observation. Before the space age, we relied on ground-based telescopes and human sketches. Now, while satellites like the Solar Dynamics Observatory capture the sun in multiple wavelengths continuously, mapping magnetic fields in exquisite detail, we have more clarity than ever, yet the sun still manages to surprise us. Here's a quirky tidbit for your sleepy amusement. In the 19th century, one astronomer speculated that sunspots might be gigantic storms with debris floating on a luminous ocean of fire, essentially cosmic seaweed. It sounds poetic and wildly incorrect, but you can almost appreciate the imagination. Today we know sunspots are magnetic phenomena where intense magnetic fields suppress convection, reducing heat transfer from below. No seaweed involved, just plasma behaving badly. What's especially curious in 2026 is the hemispheric imbalance. The northern solar hemisphere ramped up earlier in the cycle, just generating robust sunspot groups while the southern hemisphere lagged. Normally, both hemispheres roughly mirror each other over time, even if slightly out of phase. This time, the gap is wider. The magnetic equator, the invisible boundary dividing north and south magnetic dominance, appears subtly skewed. You float above a massive sunspot cluster the size of several Earths combined. That's another mainstream fact. Large sunspot groups can dwarf our entire planet. In some 2026 observations, individual active regions have spanned over 200,000 kilometers. It's humbling to realize that Earth could tuck itself inside one of these dark patches and still have room to stretch. Not that you'd want to. It's not exactly beachfront property. As these spots rotate across the solar disk, they drag their magnetic fields with them. So twisted lines build tension. And when that tension releases, flares and coronal mass ejections can erupt. The placement of sunspots matters because it influences how magnetic fields connect and reconnect. Subtle changes in latitude can alter the geometry of those connections. Some researchers are quietly exploring whether changes in the sun's internal meridional flow, the slow circulation of plasma from equator to poles and back again, might explain the shifted sunspot distribution. If that conveyor belt speeds up or slows down unevenly, it can reshape where magnetic flux emerges. Helioseismology hints that these flows may not be as stable as once assumed. Historians still argue whether long-term shifts in these internal flows could precede grand solar minima, like the Maunder minimum of the 17th century, and when sunspots nearly vanished for decades. But 2026 is not a minimum. It's the opposite, an exuberant, slightly chaotic peak. So the question isn't, is the sun going quiet? But rather, why is it so enthusiastically uneven? You can almost picture the sun shrugging. It has no obligation to obey our average timelines. Plasma doesn't read prediction reports. Magnetic fields don't consult spreadsheets. And yet there's a pattern beneath the irregularities. Even with latitude quirks and hemispheric asymmetries, the fundamental butterfly drift still exists. The wings are just a little ruffled this year. The overall polarity progression still points toward a full magnetic reversal near solar maximum. The grand mechanism hasn't broken. It's improvising. You stand once more beneath the daylight sky, unaware of the exact latitude of any sunspot above you, but comforted and unsettled at the same time. Comforted because the sun has always been dynamic. Unsettled because even slight deviations ripple outward into a technological civilization balanced delicately on electromagnetic threads. 3 light jokes later, and you realize something profound. The sun's surface is not a static face, but a shifting map of magnetic tension. In 2026, that map looks just unfamiliar enough to keep scientists awake past their bedtime. And as the sunspots continue their slow march across the solar disk, some higher, some lower than expected, you sense that this is only the beginning of the story. The freckles are forming unusual constellations, and when freckles cluster, sparks tend to follow. Watch those sprawling sunspot clusters rotate toward the center of the sun's visible face, and there's a quiet tension in the data feeds. Because when magnetically complex regions drift into direct line with Earth, you are suddenly in the splash zone of whatever tantrum they decide to throw. Solar flares are the tantrums. A solar flare is a sudden, intense burst of radiation caused by magnetic reconnection, when twisted magnetic field lines snap and realign, releasing enormous energy in minutes. The most powerful flares, classified as X-class, can release energy equivalent to billions of hydrogen bombs. Cheerful thought, I know. And yet, in 2026, what has scientists raising eyebrows isn't just the number of flares, it's how quickly some of them escalate. Traditionally, forecasters rely on precursor signals, magnetic shear builds. When sunspot groups grow more complex, X-ray output creeps upward. There are warning signs, subtle but detectable. Space weather prediction centers analyze these clues carefully, but several significant flares in 2026 have erupted with surprisingly little ramp-up time. Regions that appeared moderately active suddenly unleashed strong M-class and even X-class bursts without the usual prolonged buildup signature. It's like the sun skipped the polite throat clearing and went straight to shouting. Mainstream fact: the Carrington event of 1859 remains the most powerful geomagnetic storm on record. Telegraph systems sparked, operators received shocks, and auroras were seen as far south as the Caribbean. That event was triggered by an intense solar flare and coronal mass ejection. In modern times, a similar event could disrupt satellites, GPS, and power grids. So when flares behave unpredictably, people notice. In 2026, satellite instruments monitoring X-ray flux have recorded several sharp spikes that exceeded forecast probabilities. None have reached Carrington-level extremes, but the pattern of rapid onset has challenged existing flare prediction models. Some researchers are revisiting assumptions about how magnetic energy is stored and released in Delta-class sunspot regions. You imagine hovering above one of these regions. Magnetic loops arch high into the corona, glowing in ultraviolet light. The plasma moves along field lines like traffic flowing along invisible highways. Suddenly, two loops intersect at just the wrong angle. The magnetic tension becomes unsustainable. Snap. In a fraction of a second, energy cascades outward as radiation across the electromagnetic spectrum. X-rays, ultraviolet, radio bursts. And here's the unnerving part. Radiation from a flare reaches Earth in about 8 minutes. That's the same travel time as ordinary sunlight. If a flare is strong enough, it can ionize the upper atmosphere almost instantly, disrupting high-frequency radio communications on the sunlit side of Earth. Pilots flying polar routes sometimes reroute during major events because radio blackouts can occur. In 2026, a few such reroutes have happened more abruptly than expected due to minimal flare warning. Historians still argue whether earlier observers truly grasped the connection between solar flares and geomagnetic disturbances before the 20th century. A British astronomer, Richard Carrington, did witness a brilliant white light flare in 1859 and noted a geomagnetic storm soon after. But the physics linking them took decades to untangle. Today, we understand the chain reaction far better. Yet prediction remains imperfect. A quirky tidbit for your drowsy amusement. During the early space age, some engineers worried that astronauts might literally see flashes of light from solar particle events striking their retinas. They weren't entirely wrong. Astronauts have reported light flashes caused by cosmic rays interacting with their eyes. Space is basically a glowing pinball machine. Delightful. Back in 2026, solar flare forecasting models rely heavily on magnetic field measurements from instruments like the heliosysmic and magnetic imager. But recent events suggest that magnetic complexity alone may not fully determine eruption timing. Some regions that look chaotic remain quiet. Others that appear borderline stable suddenly erupt. You can sense the frustration and fascination in the scientific community. Flares are governed by magnetohydrodynamics, a field that combines electromagnetism and fluid dynamics in superheated plasma. It's famously difficult to model. Add to that the sun's three-dimensional structure and constant motion, and you have a puzzle that resists neat solutions. And yet the sun is not malicious. It's simply efficient at releasing stored magnetic energy. In 2026, the efficiency seems slightly heightened. Rapid-fire flares from certain active regions have produced bursts of solar energetic particles that arrived at Earth sooner than expected, compressing forecast timelines. Space weather centers have had to issue alerts with tighter margins. You sit beneath the calm blue sky, unaware of the X-ray flux streaming overhead. The atmosphere protects you beautifully. Earth's magnetic field deflects charged particles, and the ozone layer absorbs harmful ultraviolet radiation. You are wrapped in invisible armor, but satellites above you do not enjoy the same cozy blanket. Electronics can be disrupted by intense radiation. Solar panels degrade faster. 3 gentle jokes later, and you might imagine the sun as a dramatic opera singer hitting unexpected high notes. The orchestra, the planets, the satellites, the astronauts must adjust mid-performance. Scientists are now examining whether the unusual sunspot latitude patterns you considered earlier are linked to these flare behaviors. If magnetic flux is emerging in slightly altered geometries, perhaps reconnection events are triggered differently. It's a subtle shift, but subtle shifts can matter in nonlinear systems. Historians still argue whether solar cycles ever truly repeat in identical fashion. The more data we gather, the clearer it becomes that each cycle has its own personality. 2026's personality feels energetic, slightly impulsive, and fond of dramatic timing. You breathe slowly, feeling the warmth of ordinary sunlight on your skin. 8 minutes ago, that light left the surface of a star crackling with magnetic tension. Somewhere up there, another active region is rotating into view. Its magnetic loops are tightening. The models are updating. And while you drift towards sleep, the sun continues rehearsing its next sudden crescendo, sometimes whispering and sometimes roaring, reminding scientists that prediction is an art practiced under a very bright, very unpredictable spotlight. The flares fade, at least for the moment, and your attention drifts deeper, past the bright surface, past the boiling granules of plasma, down into the invisible architecture that controls it all, the sun's magnetic field. Every 11 years or so, something extraordinary happens. The sun flips. Its magnetic north and south poles reverse. What was north becomes south, and what was south becomes north. This isn't metaphorical, it's measurable. The sun's global magnetic field weakens, tangles, and then reemerges with opposite polarity. It's part of the standard solar cycle, as routine, cosmically speaking, as changing the batteries in a smoke detector. Except the batteries are made of plasma, and the smoke detector is 1.4 million kilometers wide. Mainstream fact, during solar maximum, the sun's magnetic field becomes highly complex and disordered before reorganizing into a flipped configuration. This reversal has been observed consistently since systematic measurements began in the mid-20th century. It's not a rare event, it's built into the cycle. But in 2026, the flip isn't unfolding quite the way scientists expected. The magnetic reversal appears uneven between hemispheres. The northern hemisphere began weakening and shifting polarity earlier, while the southern hemisphere lagged behind. Normally, the poles reverse within months of each other. This time, the timing gap has stretched longer than forecast models predicted. It's as if one half of the sun decided to redecorate while the other half is still staring at paint samples. You imagine the sun's magnetic field as a vast, invisible bar magnet wrapped around a sphere. But unlike a simple bar magnet, the sun's field is generated by its internal dynamo, churning plasma flows in the convection zone that twist and amplify magnetic lines. Differential rotation stretches those lines around the equator, while meridional flows drag them toward the poles. Over time, the old polar fields weaken as new magnetic flux from sunspots migrates poleward, canceling and replacing them. In 2026, magnetograms, maps of magnetic field strength, show that this poleward migration is happening, but with surprising asymmetry. Some researchers suggest that variations in meridional flow speed may be responsible, and others suspect deeper dynamo fluctuations. Historians still argue whether hemispheric asymmetry during reversals signals stronger upcoming cycles or simply reflects short-term turbulence in the sun's plasma flows. The data from past cycles is suggestive, but not decisive. You float above the solar poles in your imagination. Instead of icy calm, you see magnetic field lines erupting outward, bending and reconnecting. During reversal, the polar fields weaken dramatically before rebuilding. For a time, the sun's overall magnetic shield is more chaotic, less dipole and more tangled web. That tangled phase can influence how the solar wind flows outward through the heliosphere. Here's where it gets interesting. The heliosphere, the enormous bubble carved out by the solar wind extending far beyond Pluto, is shaped by the sun's magnetic field. When the global field is orderly, the heliosphere has a smoother structure. When the field is disordered, the heliospheric current sheet, the Vishal wavy boundary separating magnetic polarities, becomes more warped. In 2026, spacecraft measurements suggest that this current sheet is particularly wavy, like a bed sheet flapping dramatically in a cosmic breeze. A quirky tidbit for your drifting mind. Some early 20th century scientists speculated that magnetic reversals on the sun might somehow trigger Earth's own magnetic pole reversals. That idea has since been thoroughly debunked. Earth's magnetic field is generated by molten iron flows in its outer core and flips on timescales of hundreds of thousands of years. The sun and Earth may be magnetically connected through space weather, but they do not share a synchronized flip schedule. No cosmic group chat coordinating pole swaps. Still, the sun's reversal matters. During this phase, increased magnetic complexity can open more pathways for energetic particles to escape. That may partly explain why 2026 has seen bursts of activity that feel abrupt. If the global field is in a transitional state, local magnetic regions may evolve differently than expected. Scientists monitor the polar field strength carefully because it's one of the best predictors of the next solar cycle's intensity. A stronger polar field at minimum tends to precede a stronger subsequent cycle. But with the asymmetry in 2026, predictions grow fuzzier. If one hemisphere rebuilds more robustly than the other, what does that mean for solar cycle 26? The models are still catching up. You sense the quiet tension in observatories around the world. And the Wilcox Solar Observatory at Stanford has tracked polar fields for decades. Its long-term data set is invaluable. In 2026, researchers pore over those measurements, comparing the slope of decline and rebound to past cycles. Some curves align, others diverge subtly. Subtle divergences are where the real debates begin. Historians still argue whether the sun's dynamo operates as a single coherent engine or as multiple loosely coupled systems in each hemisphere. If the hemispheres can drift out of sync more than previously assumed, that complicates forecasting. Perhaps the sun is less like one heartbeat and more like two drummers trying, usually successfully, to stay in rhythm. In 2026, one drummer might be improvising. You smile faintly at the thought that this colossal star, source of all earthly life, can't quite coordinate its hemispheres on schedule. It's strangely comforting. Even stars have asymmetrical days. And yet, beneath the gentle humor lies real significance. The timing and structure of the magnetic flip influence space weather conditions throughout the solar system. Mars, lacking a global magnetic field, is especially exposed. Spacecraft on a route to the moon or beyond must account for changing radiation environments. As you stand under your quiet sky, you would never know that the sun's magnetic poles are mid-transition, that billions of tons of plasma are reshaping an invisible field extending across billions of kilometers. The sunlight feels the same. The warmth is steady, but deep within that blazing sphere, the great magnetic engine is shifting gears, slightly unevenly, slightly unpredictably, reminding scientists that even well-known cycles can bend at the edges. And as the reversal continues, one hemisphere catching up to the other, the question lingers softly in the background. Is this just a quirky phase of an ordinary flip, or a hint that the solar dynamo itself is entering a subtly new chapter? You let that question float upward, like a magnetic field line stretching into space, unresolved for now, shimmering quietly above your sleepy world. As the sun's magnetic poles wobble through their uneven reversal, something else begins to surge outward. Not just radiation, not just flares, but enormous clouds of charged plasma hurled into space. Coronal mass ejections, CMS. If solar flares are lightning flashes, CMS are the cannon shots. A coronal mass ejection occurs when vast loops of magnetic field in the sun's corona become unstable and erupt, launching billions of tons of plasma into space at speeds that can exceed 2,000 kilometers per second. That's fast enough to travel from the sun to Earth in as little as 15 to 18 hours. Normally, it takes 2 to 3 days. In 2026, scientists have observed a noticeable uptick in both the frequency and velocity of Earth-directed CMEs compared to early cycle predictions. Mainstream fact: CMS are the primary drivers of major geomagnetic storms on Earth. When a CME's magnetic field interacts strongly with Earth's magnetosphere, especially if it's oriented southward, it can trigger powerful disturbances, energizing auroras, and inducing currents in power grids. This is well established, studied extensively since the space age began. What feels different in 2026 isn't that CMEs exist. It's that clusters of them have erupted in close succession from magnetically complex regions that models previously labeled moderate risk. Some have traveled faster than expected, compressing forecast windows. Space weather prediction centers have had to issue alerts with tighter turnaround times, occasionally updating arrival estimates multiple times in a single day. You imagine standing in orbit above Earth as a CME approaches. First comes the shock front, a ripple in the solar wind. Then the magnetic cloud arrives, a twisted flux rope of plasma carrying embedded magnetic fields. When that field meets Earth's own, the interaction depends on alignment. If the CME's magnetic field points southward, opposite Earth's northward field, reconnection occurs efficiently. An energy pours into the magnetosphere. It's cosmic Velcro. And in 2026, some of that Velcro is sticking particularly well. In May 2026, a series of CMEs erupted within days of each other, creating what researchers call CME cannibalism. One fast CME overtook a slower one ahead of it, merging into a stronger combined structure. This is a known phenomenon, but the clustering surprised forecasters who had anticipated a smoother tapering of activity near the predicted peak. When merged CMEs reach Earth, their effects can be amplified. Historians still argue whether similar CME clustering events in past centuries contributed to extreme geomagnetic storms that were poorly documented due to limited instrumentation. Before satellites, our understanding came from magnetometers and eyewitness aurora reports. And the Carrington event likely involved a particularly well-aligned CME. But how many near misses went unnoticed? The historical record is incomplete. You drift back to the sun's corona, the outer atmosphere visible during a total solar eclipse, as a pearly halo. The corona is paradoxically hotter than the surface, reaching millions of degrees Celsius. That mystery, the coronal heating problem, remains partially unsolved. Tiny magnetic reconnection events called nanoflares may contribute. In 2026, high-resolution observations suggest heightened small-scale magnetic turbulence in active regions that later produced major CMEs. Researchers are exploring whether increased microinstability precedes large-scale eruptions more reliably than previously thought. A quirky tidbit for your sleepy amusement. During early solar research, some scientists believe CMEs might be literal chunks of the sun breaking off and flying through space like fiery cannonballs. Thankfully, the sun is not shedding pieces like a poorly assembled pastry. CMS are plasma, ionized gas, guided by magnetic fields, not solid fragments. No flaming solar meatballs headed your way. Still, the scale is staggering. A single CME can carry 1 billion tons of matter. That's roughly the mass of a mountain, flung outward by magnetic forces alone. And in 2026, several have been clocked at higher than average speeds for this stage of the cycle. Not unprecedented, but statistically notable. When these clouds strike Earth, auroras bloom. In recent months, observers have reported vivid displays at latitudes lower than usual. Once the sky glows green and red over regions that don't typically expect celestial light shows, social media fills with astonished photos. Meanwhile, power grid operators quietly monitor transformer loads. 3 gentle jokes later, and you realize something profound. The same event that paints the sky in shimmering beauty can also rattle the infrastructure beneath your feet. Cosmic art and engineering anxiety, all in one package. Space agencies are particularly attentive. Satellites in geostationary orbit sit exposed to enhanced radiation during CME impacts. Increased drag in low Earth orbit can alter trajectories. Astronauts aboard the International Space Station sometimes move to more shielded areas during significant solar particle events. In 2026, precautionary steps have been taken more frequently than forecast planners initially expected for this phase of the cycle. Historians still argue whether humanity's technological vulnerability to solar storms is underestimated. Some studies suggest a truly extreme geomagnetic event could cause prolonged regional power outages. Others argue modern grid protections are more robust than worst-case scenarios imply. The debate continues, grounded in modeling and risk analysis. Meanwhile, the sun continues its outward exhalations. The heliosphere pulses with each CME, sending ripples far beyond Earth, past Mars, past Jupiter, toward the outer reaches of the solar system. Spacecraft like Parker Solar Probe and Solar Orbiter, operating closer to the sun than ever before, are capturing unprecedented detail of CME formation and structure. In 2026, their data streams are invaluable, revealing the internal magnetic twists of ejected plasma clouds before they expand into interplanetary space. You stand once more under your ordinary sky. The wind on your face is terrestrial, not solar. The warmth is steady. Yet above you, invisible magnetic clouds occasionally sweep past, bending Earth's magnetic field like tall grass in a storm. The sun is not raging uncontrollably. It is simply expressing its magnetic complexity with a little more enthusiasm than forecast. CMAs are surging, clustering, accelerating just enough to keep scientists recalculating. And as one more massive arc of plasma lifts from the corona, curving outward in a slow, majestic arc before snapping free into space, you sense that this is the sun at its most dynamic, breathing out mountains of magnetized fire, reshaping the space around you in ways both beautiful and quietly profound. As those massive clouds of plasma surge outward, something subtler, but just as important, flows continuously behind them. You can't see it, you can't feel it, yet it brushes past Earth every second of your life. The solar wind. Imagine the sun not just erupting occasionally, but constantly exhaling. The solar wind is a steady stream of charged particles, mostly protons and electrons, escaping the sun's corona and streaming outward through the solar system. It travels at speeds typically ranging from 300 to 800 kilometers per second. At those velocities, the wind from the sun reaches Earth in about 1 to 4 days. Mainstream fact: the solar wind shapes the heliosphere, the vast magnetic bubble that envelops all the planets and extends well beyond Pluto. Without it, interstellar space would press closer. With it, we exist inside a constantly shifting, electrically active cocoon. In 2026, instruments monitoring the solar wind, both near Earth and closer to the sun, have detected changes in its speed and structure that weren't fully anticipated. Not dramatically higher across the board, but punctuated by more frequent high-speed streams emerging from coronal holes. Coronal holes are darker, cooler regions in the sun's corona, where magnetic field lines open outward into space rather than looping back down. These open khutut allow particles to escape more freely, producing fast solar wind streams. During solar minimum, coronal holes are often concentrated near the poles. During maximum, they can appear at lower latitudes. And here's where things get interesting in 2026. Equatorial coronal holes have been more persistent and expansive than forecast models suggested for this phase of the cycle. That means high-speed streams are sweeping across Earth's orbit more often. You imagine Earth drifting through space like a boat crossing invisible currents. When a fast solar wind stream overtakes slower wind ahead of it, the interaction creates a co-rotating interaction region, essentially a compressed zone of enhanced magnetic field and density. When these regions reach Earth, they can trigger moderate geomagnetic storms, even without a dramatic CME. It's less cannon blast, more steady gale. But a steady gale can still rock the ship. Historians still argue whether long-term variations in solar wind strength influence cosmic ray penetration into Earth's atmosphere in ways that subtly affect cloud formation. The connection remains debated. Some studies suggest correlations. Others find the effect too small to be climatically significant. The sun's influence on Earth's climate is real but complex, and 2026's solar wind variations are being studied carefully in that broader context. Meanwhile, spacecraft are providing a front-row seat. NASA's Parker Solar Probe, dipping closer to the sun than any mission before it, has been measuring solar wind acceleration zones directly. In recent passes, it has observed abrupt switchbacks, sudden reversals in magnetic field direction embedded in the wind. These switchbacks appear more common near active regions. In 2026, as solar activity intensifies, researchers are analyzing whether the increased magnetic complexity is feeding more of these turbulent structures into interplanetary space. A quirky tidbit to drift on. When the solar wind was first proposed in the 1950s by physicist Eugene Parker, many scientists were skeptical. The idea that the sun continuously blew a supersonic wind seemed radical. Now it's foundational astrophysics. Poor Parker had to defend the concept vigorously. Imagine arguing that the sun is basically cosmic breath and being told, that sounds unlikely. History vindicated him. Back in the present, measurements near Earth have recorded several intervals in 2026 where solar wind speeds exceeded 750 kilometers per second outside of major CME events. That's on the high end for coronal hole streams. And these fast flows compress Earth's magnetosphere on the day side, and stretch it into a longer tail on the night side. Satellites in certain orbits experience fluctuating conditions as magnetic boundaries shift. You picture Earth's magnetosphere like a windsock in a steady breeze. When the wind intensifies, the sock snaps taut. The boundary where solar wind pressure balances Earth's magnetic field, the magnetopause, moves closer to the planet during strong gusts. In extreme cases, geostationary satellites can briefly find themselves outside the protective boundary. In 2026, a few such compressions have approached that threshold, prompting close monitoring. 3 light jokes later, and you might imagine Earth muttering politely, "Could you not?" as another high-speed stream arrives unannounced. But the interaction is ancient. Long before satellites, the solar wind was sculpting Earth's auroras and subtly sputtering atoms from the upper atmosphere. What makes 2026 notable is not a single overwhelming event, but a pattern. More frequent fast streams layered atop elevated flare and CME activity. It's the stacking of effects that captures scientific attention. Historians still argue whether the sun's internal dynamo can enter phases where open magnetic flux, the kind that feeds coronal holes, temporarily dominates over closed loops. If so, that could explain periodic enhancements in high-speed wind streams. The current asymmetry in the magnetic reversal may be playing a role. If polar fields are rebuilding unevenly, open flux distribution could shift accordingly. You stand under a tranquil evening sky. The stars begin to emerge, faint against the lingering twilight. Above you, the solar wind continues its invisible flow, carrying magnetic ripples across millions of kilometers. It brushes past Earth's field lines, sometimes gently, sometimes with a bit more insistence than forecast. The sun, in 2026, is not just flaring and ejecting, it's breathing differently, slightly faster here, slightly more turbulent there, enough to reshape space weather expectations. And as you listen to the imagined whisper of that endless stream of particles rushing through space, you begin to understand. The sun's behavior isn't defined by single dramatic explosions alone. It's the constant wind, the subtle shifts in flow, the cumulative pressure of invisible currents that make scientists pause and recalibrate their understanding of our restless star. As those high-speed solar winds sweep past Earth, brushing the magnetosphere like an unseen tide, something beautiful begins to happen. The sky lights up. Auroras, those shimmering curtains of green, red, and violet, have always belonged mostly to high latitudes. If you live near the Arctic Circle, they are a familiar winter companion. But in 2026, the auroras have been wandering. Mainstream fact: auroras occur when charged particles from the sun are guided by Earth's magnetic field toward the polar regions, where they collide with atoms in the upper atmosphere. Oxygen emits green or red light depending on altitude, while nitrogen contributes purples and blues. It's atomic physics performing interpretive dance at 100 kilometers above your head. Normally, the auroral oval hugs the poles. But during geomagnetic storms, especially those triggered by strong CMEs or fast solar wind streams, the oval expands toward lower latitudes. In 2026, that expansion has happened more frequently than forecasters anticipated at this stage of the solar cycle. You imagine standing somewhere far south of where auroras typically roam, maybe in the American Midwest, Southern Europe, or parts of East Asia, and suddenly the northern horizon begins to glow faint green. Social media erupts. People step outside in pajamas. Neighbors who have never discussed space weather in their lives suddenly become amateur heliophysicists. And honestly, who can blame them? The sky is putting on a show it wasn't supposed to perform. In early 2026, our several moderate geomagnetic storms reached G3 levels on NOAA's 5-point scale, strong enough to push auroras into latitudes that hadn't seen them in years. Not unprecedented, but more clustered than models had forecast. It's that clustering again. The stacking of elevated solar wind speeds, multiple CMEs, and a magnetosphere already stirred from prior impacts. Historians still argue whether ancient accounts of blood-red skies at unusually low latitudes correspond to rare extreme geomagnetic storms or to atmospheric phenomena like volcanic dust. In 1770, records from Japan and China describe auroras seen for 9 consecutive nights at low latitudes. Some researchers suspect a massive solar event rivaling or exceeding the Carrington event may have been responsible. The sun has surprised humanity before. In 2026, however, the difference is instrumentation. Ground magnetometers, satellite detectors, and real-time solar imaging allow scientists to trace the chain of cause and effect with precision. When a CME leaves the sun, its speed and magnetic orientation are estimated. When it arrives, magnetometers measure the sudden impulse. Then the auroral oval swells. It's a cosmic domino effect, now visible in data as clearly as in the sky. You stand beneath one of these unexpected displays. The air is cool. The stars flicker behind rippling sheets of green light. The aurora moves silently, yet you can't shake the feeling that it should make a sound, like silk being shaken out, or distant ocean waves. Fun fact, some observers have reported faint crackling sounds during intense auroras, though scientists still debate whether those sounds are truly atmospheric or psychological. There's that phrase again. Scientists still debate, because even something as well studied as the aurora holds mysteries. The precise microphysics of particle acceleration along magnetic field lines, the way electrons gain energy before plunging into the atmosphere, is still an active area of research. In 2026, satellite missions studying Earth's magnetotail have observed intensified substorm activity during periods of high solar wind speed. Substorms are smaller energy releases within the magnetosphere that can suddenly brighten auroras. More frequent high-speed streams mean more opportunities for these substorms to ignite. A quirky tidbit for your drifting mind. In medieval Europe, when auroras were sometimes interpreted as armies clashing in the heavens. In parts of Scandinavia, folklore warned children not to wave at the lights lest they swoop down and carry them away. Considering the sun is currently behaving like an enthusiastic plasma engine, you can almost sympathize with the drama. But beneath the beauty lies physics. When solar wind pressure increases, Earth's magnetic field compresses, energy is stored in the stretched magnetotail on the night side. Eventually, magnetic reconnection occurs in the tail, flinging particles back toward the poles. The result, a sudden auroral brightening. In 2026, magnetotail reconnection events have appeared more frequent during extended high-speed stream intervals. 3 light jokes later, and you might picture Earth's magnetosphere as a rubber band being pulled and released repeatedly. Pull, snap, glow, repeat. What makes this year distinct is not a single apocalyptic storm. It's the repeated reach of auroras into places that rarely see them. Power grid operators take note. Aviation authorities monitor polar routes. Even satellite operators adjust expectations for drag and radiation exposure. Historians still argue whether society today is more resilient to geomagnetic storms than in 1859, or simply more dependent on fragile technology. In 2026, every unexpected aurora is both a spectacle and a reminder. You breathe in the cool night air as green arcs ripple overhead. The same solar wind that accelerated electrons down magnetic field lines has traveled 150 million kilometers to reach this moment. It began as turbulence in a coronal hole or the shock front of a CME. Now it paints the sky above your quiet street. It's easy to forget that the aurora is a symptom, a visible echo of invisible forces. The sun is acting differently, not violently, not catastrophically, but energetically enough to stretch the auroral boundary again and again. And as the lights shimmer, fade, then flare once more, you feel both small and strangely connected. The star that warms your days is also writing luminous poetry across your nights. In 2026, that poetry is wandering farther than expected, crossing borders of latitude as casually as sunlight crosses your window in the morning. The sky grows darker. The glow softens. But you know now that above the calm facade of ordinary daylight, invisible rivers of charged particles continue to flow. Sometimes quietly, sometimes with enough vigor to turn the heavens green in places that rarely look up expecting magic. As the auroras wander farther from the poles, painting unfamiliar skies in green and crimson, something less poetic begins to happen far above your head. Satellites start feeling the drag, not emotional drag, orbital drag. Though if satellites had feelings, 2026 might be testing their patience. Mainstream fact: when solar activity increases, Ultraviolet and X-ray radiation heat Earth's upper atmosphere, particularly the thermosphere. As it heats, it expands. That expansion increases atmospheric density at altitudes where many satellites orbit, especially in low Earth orbit between about 300 and 600 kilometers. Increased density means increased drag. Increased drag means satellites lose altitude faster. In 2026, and with solar activity exceeding earlier forecasts, thermospheric density has risen more than some mission planners initially budgeted for this stage of the cycle. It's not catastrophic, but it is measurable. Satellite operators have had to perform orbital adjustments sooner than planned. You imagine a satellite gliding smoothly around Earth, solar panels extended like wings. It expects a certain amount of atmospheric resistance, barely a whisper of particles brushing its hull. But as solar ultraviolet output ticks upward, the thermosphere puffs outward like a balloon warmed by sunlight. Suddenly, that whisper becomes a noticeable tug. The satellite's orbit begins to decay slightly faster. Engineers on the ground notice subtle changes in tracking data. They calculate fuel usage for course corrections. Every adjustment costs propellant. Propellant is finite. In February 2022, during the early rise of Solar Cycle 25, a batch of newly launched satellites was lost because an unexpected geomagnetic storm increased atmospheric drag, causing them to re-enter before they could raise their orbits. That event served as a warning. By 2026, operators are far more cautious, but the sun's above forecast activity keeps everyone attentive. Historians still argue whether the rapid growth of satellite constellations in low Earth orbit has outpaced our ability to model space weather risks accurately. With thousands of small satellites now circling Earth, even modest increases in drag can complicate collision avoidance calculations. The more objects you have up there, the more carefully you must track them when the atmosphere swells. And swell it has. Measurements from satellites that monitor thermospheric density, like the timed mission and various drag-sensitive spacecraft, show elevated density levels during extended periods of solar wind enhancement in 2026. Not unprecedented for solar maximum, but earlier and more sustained than initial models suggested. You picture the upper atmosphere like a breathing lung. During solar minimum, it exhales, shrinking slightly. During maximum, it inhales, expanding outward. In 2026, the inhale feels deeper than expected at this stage of the breath. A quirky tidbit for your drifting thoughts. In the 1970s, NASA's Skylab space station re-entered Earth's atmosphere earlier than planned, partly because of higher-than-expected solar activity increasing atmospheric drag. Engineers had anticipated a quieter sun. The sun had other plans. The Skylab's fiery descent scattered debris across Australia. No one was harmed, but it was a dramatic reminder that even small changes in solar output can alter orbital lifetimes. Today's satellites are smaller, more numerous, and often equipped with propulsion systems for orbit maintenance. But not all of them carry large fuel reserves. Some tiny satellites rely on passive drag models and limited maneuvering capability. In 2026, operators of such spacecraft are recalculating mission durations in light of the sun's enthusiastic behavior. And then there's radiation. Elevated solar activity increases the flux of energetic particles in near-Earth space. Satellites passing through regions like the South Atlantic anomaly, a weak spot in Earth's magnetic field, already face heightened radiation exposure. During active solar periods, wave background conditions can intensify. Electronics experience more single-event upsets, tiny glitches caused by energetic particles flipping bits in memory. 3 light jokes later, and you might imagine satellites wearing tiny helmets, bracing against a gusty solar forecast. But this isn't merely whimsical. In 2026, satellite anomaly reports have ticked slightly upward during periods of clustered solar events. Nothing apocalyptic, no global blackout of space infrastructure, but enough to reinforce how tightly modern life is woven into space weather conditions. GPS timing, weather forecasting, communications, Earth observation, all depend on spacecraft operating within a delicately balanced environment. Historians still argue whether our increasing reliance on satellite networks represents a vulnerability or a triumph of engineering resilience. Likely both. Modern spacecraft are shielded, hardened, and monitored more carefully than ever before. Yet the sheer scale of orbital infrastructure means cumulative risk grows alongside capability. Meanwhile, as the thermosphere expands, space debris experiences altered drag profiles as well. Some debris decays faster and re-enters, which is actually beneficial. But differential drag can shift orbital paths unpredictably, complicating tracking models. In 2026, space traffic management teams are paying close attention to these density fluctuations. You stand beneath a clear daytime sky, unaware of the subtle thickening happening 400 kilometers above you. To you, the air feels the same. Birds fly, and planes cruise. But far higher, satellites skim through a slightly denser veil than planners expected for this moment in the cycle. The sun's extra ultraviolet output, barely perceptible at ground level, is enough to warm and expand the fringes of Earth's atmosphere. It's a quiet consequence of heightened solar activity, not dramatic like an aurora, not cinematic like a CME, just persistent, and persistence matters. In 2026, the sun isn't blasting civilization apart. It's nudging, heating, tugging, enough to require mid-course corrections, enough to shorten some orbital lifetimes, enough to remind engineers that every mission plan includes a variable labeled solar activity, and that variable has decided to stretch beyond its earlier estimate. As you settle into the calm of evening, or perhaps checking your phone's GPS or streaming a show that depends on satellite relays, you are unknowingly benefiting from a quiet choreography of adjustments happening overhead. Tiny thrusters fire, trajectories are recalculated, radiation monitors tick, and all because 150 million kilometers away, a star is running slightly hotter in ultraviolet, slightly faster in wind, slightly more magnetically tangled than expected. The satellites endure, for now. But they are listening, just like the scientists are, to the subtle change in the sun's breath. As satellites adjust their orbits and radiation monitors tick a little faster, something far less visible, but potentially more consequential, begins to hum quietly on the ground. Power grids. You don't see them. You don't hear them. But beneath streets and stretching across countrysides, the high-voltage transmission lines form vast conductive loops. And when Earth's magnetic field is disturbed by solar activity, those loops can pick up unwanted guests, geomagnetically induced currents, or GICs. Mainstream fact: during strong geomagnetic storms, rapid fluctuations in Earth's magnetic field can induce electric currents in long conductors like power lines and pipelines. In March 1989, a powerful solar storm caused a blackout in Quebec, leaving millions without power for 9 hours. Transformers overheated, protective systems tripped. It was one of the clearest modern demonstrations of space weather affecting infrastructure. In 2026, no such catastrophic blackout has occurred. But grid operators are on alert more frequently than forecast planners initially expected for this stage of the solar cycle. Would you imagine Earth's magnetosphere as a protective shield? When a CME or high-speed solar wind stream strikes, that shield flexes and vibrates. Those vibrations propagate down into the ionosphere and through Earth's crust. Changing magnetic fields induce electric fields at ground level. In regions with certain geological structures, like highly resistive bedrock, those electric fields can drive currents through power grids. It's basic electromagnetic induction. Faraday would nod approvingly. During the clustered geomagnetic storms of 2026, monitoring stations in high-latitude regions have recorded elevated GIC activity. Not record-breaking, not grid-melting, but enough to prompt precautionary measures. Operators have adjusted load flows, redistributed power, and temporarily reduced transformer stress during peak disturbances. Will historians still argue whether the risk of an extreme, once-in-a-century geomagnetic storm is adequately mitigated in modern grids? Some studies warn that a Carrington-level event today could damage multiple large transformers, components that are expensive and slow to replace. Others argue that grid hardening, improved forecasting, and operational protocols significantly reduce that risk. The debate continues, grounded in modeling, engineering studies, and a healthy respect for the unknown. In 2026, the sun's heightened activity has meant more frequent geomagnetic storm watches. Each time a CME is detected heading earthward, grid control rooms receive alerts. Forecasts estimate the storm's strength based on solar wind speed and magnetic orientation. The crucial factor is the BZ component, the north-south orientation of the incoming magnetic field. If it turns strongly southward, Earth's magnetosphere reconnects more efficiently, allowing energy to pour in. You picture a control room lit by screens showing real-time magnetometer readings. Lines flicker. Operators speak calmly, methodically. They've trained for this. The sun's unpredictability isn't new, but the clustering in 2026 keeps them attentive. A quirky tidbit to drift on. In the early days of telegraph systems in the 19th century, operators sometimes disconnected their batteries during geomagnetic storms and found that aurora-induced currents alone could power the lines briefly. Messages were sent using the sun's electricity. Free energy, courtesy of a magnetically excited star. Delightful, slightly terrifying. Now today's grids are vastly more complex. High-voltage transformers are particularly sensitive to sustained GICs because those currents can cause half-cycle saturation, overheating, and long-term damage. In 2026, transformer monitoring data in vulnerable regions, like parts of Canada and Scandinavia, has shown elevated but manageable stress levels during strong storms. 3 gentle jokes later, and you might imagine transformers sighing dramatically. Again? Really? As another CME arrives on schedule. But the seriousness remains. What makes 2026 noteworthy is not a single overwhelming geomagnetic storm. It's the repeated near-threshold events, multiple G2 and G3 level storms in relatively close succession, each one manageable on its own. Together, they form a pattern that challenges earlier expectations of a more moderate solar maximum. Historians still argue whether our increasing electrification, electric vehicles, renewable energy integration, decentralized grids, makes us more resilient or more exposed to space weather disturbances. Renewable systems can be modular and distributed, which helps, but long transmission lines remain essential in many regions, and long lines are precisely what geomagnetic fluctuations exploit. Meanwhile, pipeline operators also monitor GICs because induced currents can accelerate corrosion in metal pipelines. It's another quiet interaction between cosmic forces and human infrastructure, invisible fields dancing through steel buried underground. You sit comfortably in your home, lights glowing steadily. The hum of electricity feels constant, dependable. And it is, because engineers and forecasters are watching the sun with greater intensity this year. Space weather prediction models have been updated in real time as 2026 unfolds. The sun is not attacking. It is behaving energetically, perhaps more energetically than predicted. And that difference between predicted and actual matters when billions of people rely on stable power. During one particularly active week in mid-2026, a series of fast solar wind streams combined with a CME impact, producing a prolonged geomagnetic disturbance. Grid operators implemented mitigation protocols for nearly 48 hours. Power flowed uninterrupted, but the vigilance was palpable. You sense the interconnectedness now. Sunspots twist, flares erupt, CMS launch, solar wind accelerates, Earth's magnetosphere flexes, auroras bloom, satellites adjust, and deep beneath your feet, transformers hum a little more cautiously. It's a chain reaction spanning 150 million kilometers, linking nuclear fusion at the sun's core to the quiet glow of your bedside lamp. And in 2026, that chain is being tugged slightly more often than the forecast once suggested. Not broken, not snapped, just tested. As you drift towards sleep, the grid remains steady, the lights unwavering. But somewhere in monitoring centers across the globe, teams continue watching magnetometer traces scroll across their screens, aware that the star overhead has entered a phase of spirited improvisation, and the question lingers softly in the background. How many more near-threshold storms will this cycle deliver before the sun finally settles into its gradual decline? For now, the current keeps flowing. The hum continues. Noah and the sun, 150 million kilometers away, remains just energetic enough to keep everyone listening. As transformers hum steadily and satellites correct their paths, another question begins to circulate. Quieter, more cautious, and far more controversial. Is any of this touching the climate? You feel the warmth of sunlight on your skin, and it seems constant, reliable, and in many ways it is. Mainstream fact: the sun's total energy output, known as total solar irradiance, varies by only about 0.1% over the course of a typical 11-year solar cycle. That's remarkably stable for a nuclear fusion reactor the size of 1 million Earths. Compared to human-driven greenhouse gas forcing, that 0.1% fluctuation is small, but small does not mean irrelevant. In 2026, as solar activity has surged beyond early forecasts, mine atmospheric scientists are carefully examining whether subtle changes in ultraviolet radiation and solar-wind interactions might be influencing the upper atmosphere in measurable ways, not causing heat waves, not rewriting climate models overnight, but nudging certain atmospheric layers. Ultraviolet radiation increases more dramatically than total visible light during solar maximum. That extra UV is absorbed in the stratosphere, where it influences ozone chemistry. When UV rises, ozone production can increase in certain layers, which in turn slightly alters temperature gradients. These shifts can ripple into atmospheric circulation patterns. The effects are subtle and complex, more like adjusting the tuning of a violin string than smashing the instrument. Historians still argue whether periods like the Maunder minimum, the prolonged sunspot lull from about 1645 to 1715, contributed significantly to the Little Ice Age in Europe. Some studies suggest reduced solar activity played a minor role alongside volcanic eruptions and internal climate variability. Others argue the solar contribution was modest at best. The debate continues, nuanced and data-heavy. In 2026, we are not in a minimum. We are in a lively maximum. So the question is different. Could heightened solar UV and energetic particle activity subtly modulate atmospheric dynamics? You imagine layers of Earth's atmosphere stacked like translucent blankets. The troposphere, where weather happens, the stratosphere above it, then the mesosphere and thermosphere. Solar variability touches each layer differently. Increased solar activity heats and expands the thermosphere dramatically, something satellites are already experiencing as drag. In the stratosphere, changes in UV absorption can influence jet stream behavior in subtle ways. But here's the key point. Modern climate science overwhelmingly attributes current global warming trends to greenhouse gas emissions, not solar variability. Solar output has been monitored by satellites since 1978, and long-term trends show no sustained increase matching the rapid rise in global temperatures. That's well established. So why are scientists still paying attention in 2026? Because short-term variability still matters. Seasonal atmospheric patterns, regional circulation shifts, and space weather-driven chemistry changes are active areas of research. When the sun behaves more energetically than predicted, and researchers take the opportunity to refine models. More data during stronger than expected peaks helps test theories. A quirky tidbit for your drifting thoughts. In the early 20th century, some researchers seriously proposed that sunspots might directly influence human behavior, everything from stock market trends to political unrest. Spoiler alert, there's no solid evidence that your mood swings are solar-powered. If you're grumpy, it's probably not a sunspot's fault. Probably. Still, there is one intriguing area under renewed scrutiny in 2026. Cosmic rays. When solar activity is high, the enhanced solar wind and magnetic field better shield Earth from galactic cosmic rays. When activity is low, more cosmic rays penetrate the atmosphere. Some hypotheses suggest cosmic rays may influence cloud formation by ionizing atmospheric particles. Historians still argue whether the cosmic ray cloud connection is strong enough to meaningfully affect climate. Experimental results have been mixed. Some laboratory studies show ionization can assist aerosol formation under controlled conditions. Translating that into global cloud cover changes is far more complicated. During 2026 active phase, cosmic ray counts measured by ground-based neutron monitors have dipped slightly, as expected during solar maximum. Researchers are comparing cloud satellite data with these measurements, searching for correlations. So far, any effect appears subtle, but subtle patterns are where atmospheric science often lives. You stand beneath a sky that feels utterly ordinary. The temperature depends on your season, your hemisphere, more so your weather system, not on whether the sun's magnetic field is asymmetrical this month. Yet high above, in layers you never see, chemical reactions shift ever so slightly in response to ultraviolet fluctuations. Three gentle jokes later, and you might imagine atmospheric scientists squinting at spreadsheets saying, is that signal real, or is the atmosphere just being dramatic again? The responsible answer is patience. Climate operates on long timescales. Solar cycles are short by comparison. In 2026, the sun's unexpected vigor offers an opportunity, not a crisis, to refine understanding of solar atmospheric coupling. Meanwhile, public conversations sometimes blur distinctions. When auroras appear at low latitudes or solar storms make headlines, speculation can flare up online about dramatic climate shifts. Scientists respond carefully by, emphasizing scale. The sun influences Earth profoundly, but within bounds that are well studied. The real story of 2026 is not that the sun is rewriting climate physics. It's that it is slightly exceeding short-term activity forecasts, giving researchers a richer data set than anticipated. You feel the steady warmth again. The same star that fuels photosynthesis, powers weather systems, and lights your mornings is pulsing with magnetic complexity. But its total brightness remains remarkably consistent. The dance of climate involves oceans, greenhouse gases, volcanic aerosols, and internal variability, far more than a 0.1% solar fluctuation. And yet, in the upper reaches of the atmosphere, tiny changes ripple quietly. The sun's ultraviolet breath thickens ozone here, warms a layer there. Space weather brushes the climate system's outer edges, not steering the ship, but tapping lightly on its hull. As you drift towards sleep, the debate continues in laboratories and universities. Data accumulates. Models update. Historians still argue about the past. Scientists carefully measure the present. The sun in 2026 is energetic, yes, but not a climate puppet master. It is a dynamic star offering researchers a vivid reminder that even small variations in a steady furnace can illuminate the fine threads connecting space and sky. And those threads, delicate and complex, shimmer quietly above you tonight. While climate scientists refine their models and grid operators monitor transformer loads, another group of researchers is listening for something far subtler than flares or solar wind. They are listening to the sun's vibrations. And not with ears, of course. The sun does not hum audibly across space, though if it did, it would probably be the loudest lullaby in the solar system. Instead, scientists use heliosysmology, the study of pressure waves rippling through the sun's interior. Mainstream fact: the sun oscillates in millions of different modes, driven by convection beneath its surface. These pressure waves, called P modes, cause the surface to rise and fall by a few meters over periods of about 5 minutes. Instruments measure tiny Doppler shifts in light to detect these motions. By analyzing them, scientists can infer conditions deep inside the sun, much like seismologists use earthquakes to study Earth's interior. In 2026, heliosysmic data has shown subtle deviations from expected flow patterns, particularly in the sun's internal rotation and meridional circulation. Not dramatic disruptions, but enough to suggest that the solar dynamo may be operating with slightly altered timing compared to earlier models. You imagine the sun sliced open like a glowing cross-section. At the core, nuclear fusion fuses hydrogen into helium at temperatures around 15 million degrees Celsius. Above that lies the radiative zone, where energy moves outwards slowly through radiation. Then comes the convection zone, the outer 30% by radius, where hot plasma rises and cooler plasma sinks in enormous rolling currents. It's in this convection zone that the magnetic dynamo lives. Differential rotation, faster at the equator, slower at the poles, stretches magnetic field lines. Meridional flows transport magnetic flux poleward. The interplay between these motions generates the 11-year cycle. Heliosysmology allows scientists to measure the speed of these internal flows. In 2026, some analyses suggest that the equator-to-pole circulation in one hemisphere may have accelerated slightly compared to pre-cycle forecasts. That could help explain the hemispheric asymmetry you encountered earlier during the magnetic pole reversal. Historians still argue whether long-term variations in these deep flows are responsible for grand solar minima and maxima. Data spanning only a few decades of detailed helioseismic observation limits certainty. We are, in cosmic terms, still beginners at listening to our star's heartbeat. You picture scientists examining colorful maps of internal rotation rates, bands of faster and slower plasma migrating through the sun's interior. These bands, sometimes called torsional oscillations, move over the course of the solar cycle. In 2026, their progression appears slightly ahead of schedule in certain latitudes, as if the sun's internal conveyor belts are running a bit briskly. A quirky tidbit to carry gently into your imagination. The sun's oscillations can be converted into sound waves, sped up dramatically into the audible range. When played back, they resemble eerie rising tones, like a minimalist sci-fi soundtrack. Technically accurate music, performed by a star. No concert tickets required. Back in the data, researchers are also examining subtle frequency shifts in oscillation modes. During solar maximum, P-mode frequencies tend to increase slightly due to changes in magnetic activity near the surface. In 2026, those shifts have been tracking with the elevated activity, but in some bands the changes are slightly larger than predicted. What does that mean? Possibly that near-surface magnetic fields are stronger or more widespread than anticipated, or that internal flows are redistributing magnetic energy differently this cycle. The precise interpretation remains under study. Historians still argue whether the solar dynamo operates primarily in a thin shear layer at the base of the convection zone, the tachocline, or whether significant dynamo action occurs throughout the convection zone itself. The answer affects how sensitive the cycle might be to variations in internal flow speed. In 2026, as flow measurements show slight anomalies, those theoretical debates feel newly relevant. You imagine floating deep within the convection zone, surrounded by churning plasma cells the size of continents. Hot material rises in luminous plumes. Cooler plasma sinks in darker lanes. Magnetic fields thread through this motion, stretched and twisted like taffy. 3 gentle jokes later, and you might picture the sun as a cosmic lava lamp with a doctorate in electromagnetism. But beneath the humor lies profound significance. If internal flow speeds vary even by a few percent, the timing and strength of future solar cycles could shift. The fact that cycle 25 ramped up more strongly than early forecasts may reflect subtle dynamo adjustments that helioseismology is only now revealing. Meanwhile, with spacecraft like the Solar Dynamics Observatory and ground-based networks continue feeding real-time oscillation data into computational models. Supercomputers attempt to simulate magnetohydrodynamic flows in 3 dimensions, an extraordinarily complex task. Even the most advanced simulations struggle to capture the full turbulence of the sun's interior. In 2026, the mismatch between predicted and observed activity has sharpened interest in refining those models. Researchers are revisiting assumptions about how magnetic flux tubes rise through the convection zone before emerging as sunspots. Perhaps the buoyant ascent is faster in certain regions. Perhaps internal shear layers are more dynamic than previously estimated. You stand once more beneath an unremarkable sky. The sun above you appears constant, steady, almost serene. But deep inside, acoustic waves are ricocheting through incandescent plasma, carrying encoded messages about flow speeds and magnetic tension. The sun is not merely flaring differently. It is vibrating differently, subtly, rhythmically, measurably. And in 2026, those vibrations hint that the engine beneath the surface may be running just a little off its predicted tempo. Not broken, not unstable, just improvising. As you let that thought settle, you realize that scientists are not only watching the sun's surface eruptions, they are listening to its interior murmurs. And those murmurs suggest that the story unfolding in 2026 began long before the first unexpected flare, deep within the rolling currents of a star that has been practicing fusion for 4.6 billion years. The heartbeat continues, slightly faster here, slightly shifted there. And you, tiny beneath it all, are living in a moment when humanity can finally hear that heartbeat. And notice when it changes rhythm. If helioseismology lets you hear the sun's heartbeat, neutrinos let you eavesdrop on its core. Not the surface, not the corona. The core, where fusion actually happens. Mainstream fact, every second, in the sun's core, About 600 million tons of hydrogen are fused into helium through nuclear fusion. In that process, a tiny fraction of mass is converted into energy, according to Einstein's famous equation, E equals mc squared. Among the byproducts of this fusion are neutrinos, nearly massless, electrically neutral particles that interact so weakly with matter that trillions pass through your body every second without you noticing. They leave the sun's core almost instantly. When and while photons can take thousands to hundreds of thousands of years to random walk their way from the core to the surface, neutrinos escape in seconds. That makes them pristine messengers of what is happening right now in the sun's nuclear furnace. In 2026, neutrino observatories, like Super Kamiokande in Japan and Borsino in Italy, continue their long-term measurements of solar neutrino flux. And while no dramatic spike has been observed, researchers have reported small fluctuations consistent with the elevated magnetic activity of the solar maximum. Now let's be very clear. There is no evidence that the sun's core fusion rate is suddenly surging in a dangerous way. The sun remains extraordinarily stable on nuclear timescales. Any core-level change large enough to threaten Earth would unfold over millions of years, not months. But subtle neutrino variations correlated with solar magnetic cycles are an area of ongoing research. Historians still argue whether early discrepancies in neutrino counts, the famous solar neutrino problem discovered in the late 1960s, hinted at gaps in solar models or in particle physics. For decades, detectors measured only about 1/3 of the predicted neutrino flux. The mystery was eventually solved when physicists realized neutrinos oscillate between different types, or flavors, during their journey to Earth. The missing neutrinos weren't missing. They had simply shape-shifted. Particle physics took a bow. In 2026, with that mystery long resolved, scientists now examine whether solar magnetic activity subtly influences neutrino detection rates. Some theories propose that strong magnetic fields in the sun's outer layers could affect certain neutrino properties during transit, though any such effects appear extremely small. You imagine neutrinos streaming outward from the core in every direction, ghost-like and unstoppable. They pass through the dense radiative zone, through the churning convection zone, through the photosphere, and then into space. 8 minutes later, sunlight reaches you. But neutrinos, they reach you about 8 minutes and a few seconds after leaving the core, directly unimpeded. And you didn't feel a thing. A quirky tidbit for your drifting mind. Neutrino detectors are often built deep underground, in mines or beneath mountains, to shield them from cosmic rays. Massive tanks filled with ultra-pure water or liquid scintillator wait patiently for the rare moment when a neutrino actually interacts with an atom. Imagine building a cathedral-sized instrument just to catch a particle that almost never stops to say hello. In 2026, solar neutrino measurements remain consistent with long-standing solar models. That's reassuring, but researchers have noticed that certain neutrino detection rates vary slightly over the 11-year solar cycle. Whether this reflects solar magnetic modulation effects or detector sensitivities is still under study. Historians still argue whether any measurable neutrino flux modulation could provide predictive insight into upcoming solar cycle intensity. At present, the variations are too subtle to serve as reliable forecasting tools. But the idea remains intriguing. Could the sun's magnetic complexity leave a faint fingerprint even on particles born in its core? You drift inward again, imagining the fusion process itself. 4 hydrogen nuclei fuse through a series of steps known as the proton-proton chain reaction. Along the way, positrons and neutrinos are emitted. Gamma rays are produced. Energy radiates outward. This process has powered Earth's biosphere for billions of years. In 2026, despite the flares, the CMEs, the uneven magnetic reversal, the faster solar wind, the core remains steady. Fusion continues at a stable rate. The sun is not burning hotter in any runaway sense. Its surface magnetism may be improvising, but its nuclear engine remains astonishingly constant. 3 gentle jokes later, and you might picture the sun's core as the calm executive office, while the surface departments run around in mild chaos. Please, the core says, adjusting its fusion tie, carry on. But that surface chaos, magnetic reconnection, turbulent flows, asymmetrical reversals, may still leave tiny signatures detectable in neutrino or helioseismic data. Researchers in 2026 are cross-referencing datasets more closely than ever. Surface activity indices are compared with neutrino flux records. Oscillation frequencies are plotted alongside flare counts. The emerging picture is nuanced. The sun's interior and exterior are connected through magnetic fields and plasma flows, but the coupling is complex. Surface magnetic storms do not imply core instability. Instead, when they reflect the dynamo processes in the convection zone, layers far above the fusion engine itself. You exhale slowly, reassured. The sun's heart is steady. The flickers and bursts you followed are symptoms of magnetic choreography, not nuclear upheaval. And yet the fact that we can measure neutrinos at all, that we can confirm the fusion rate in real time, is extraordinary. In 2026, as the sun behaves more energetically than expected at its surface, neutrino detectors quietly confirm that the furnace beneath remains faithful to its 4.6 billion year routine. Historians still argue about how much more we will eventually learn from neutrinos, whether future detectors might map the core in even finer detail. Perhaps one day we'll detect subtle asymmetries in fusion rates across the core itself. For now, Azra, the data suggests remarkable stability. You stand beneath a star that is, simultaneously, wildly dynamic and profoundly steady. Magnetic fields twist unpredictably. Plasma erupts into space. Auroras wander. Satellites adjust. Power grids hum cautiously. And deep inside, fusion continues with serene persistence. As you drift toward the quiet edge of sleep, imagine those neutrinos still streaming through you, silent and indifferent, carrying proof that even when the sun acts differently on the outside, its nuclear heart remains unwavering. The surface may improvise. The core keeps time. Long before satellites, before magnetometers, before anyone knew what a neutrino was, people still watch the sun, and sometimes they notice that it behaves strangely. You drift backward now, not through space, but through time. Mainstream fact: systematic telescopic observations of sunspots began in the early 17th century, shortly after the telescope was introduced to astronomy. Galileo Galilei, Christoph Scheiner, and others documented dark spots moving across the solar disk, proving the sun rotated. Those early sketches, careful and surprisingly detailed, remain part of the scientific record today. But even before telescopes, there were hints. Ancient Chinese astronomers recorded black vapor, or black spots on the sun as early as 28 BCE, visible to the naked eye during heavy dust or mist conditions that dimmed the glare. Large sunspots can indeed be seen without magnification under the right atmospheric filtering, though please don't test that theory yourself. Your ancestors had more patience for retinal risk than you do. In 2026, as scientists puzzle over asymmetric magnetic reversals and unexpectedly energetic peaks, they are also revisiting historical records. Because the sun has surprised humanity before. The most famous example is the Maunder minimum from about 1645 to 1715. During that 70-year period, sunspots became exceedingly rare. Telescopic records show dramatic suppression of visible activity. This coincided with some of the coldest decades of the Little Ice Age in parts of Europe and North America. Rivers like the Thames froze more frequently. Winters were harsh. Historians still argue whether the Maunder minimum significantly contributed to those colder conditions, or whether volcanic eruptions and internal climate variability played a larger role. The consensus today suggests solar activity likely contributed modestly, but was not the sole driver. Still, the coincidence is striking. Now fast forward again to 2026. We are not in a grand minimum, we are in an unexpectedly lively maximum. But the comparison matters because it reminds scientists that the solar cycle is not a perfectly regular clock. Over centuries, its amplitude and duration vary. Another historical episode draws attention: the Dalton minimum from about 1790 to 1830, a period of reduced sunspot activity that followed several strong cycles. It was less severe than the Maunder minimum, but still notable. Some researchers study isotope records, like carbon-14 in tree rings and beryllium-10 in ice cores, to reconstruct solar activity long before telescopes. When solar activity is low, more cosmic rays reach Earth, increasing production of these isotopes. In 2026, scientists compare modern neutron monitor data with these long-term isotope records. The current cycle's strength does not approach the most extreme historical peaks, but it exceeds earlier 21st century averages. It suggests that the relatively quiet stretch of recent decades may not represent a long-term downward trend after all. You imagine monks in medieval monasteries recording unusual red glows in the sky, unsure whether they were witnessing divine omens or magnetic storms. In 774 to 775 CE, tree rings show a sharp spike in carbon-14 levels, indicating an intense burst of cosmic radiation. Historians still argue whether that event was caused by a massive solar proton event or a distant astrophysical phenomenon like a gamma-ray burst. The sun is a suspect, but not conclusively guilty. Hurried a quirky tidbit for your drifting mind. In the 19th century, amateur astronomers sometimes projected the sun's image onto paper and traced sunspots by hand daily, building detailed logs. Imagine the patience, day after day, sketching freckles on a blinding star. Today, spacecraft do that automatically in multiple wavelengths every few seconds. The monks would be impressed. Back in the present, researchers are using those centuries of observations to contextualize 2026's behavior. Is this cycle unusually strong in the grand historical sense? Not yet. Solar cycle 19 in the 1950s was stronger, but cycle 25 has already exceeded early predictions, reminding scientists how difficult long-range forecasting can be. Now, historians still argue whether the sun follows longer periodicities beyond the 11-year and Gleisberg, approximately 80-year cycles, perhaps 200-year or even millennial-scale rhythms. Evidence from isotopes hints at longer modulations, but disentangling solar signals from terrestrial influences is challenging. You stand beneath the same sun that medieval skywatchers feared and Renaissance astronomers sketched. The difference is that in 2026, we measure it with spacecraft grazing its corona and detectors buried underground. Yet the core truth remains: the sun has moods, long moods, short moods. The current mood is energetic, slightly unpredictable, enthusiastic in flare production, generous with auroras. But history tempers alarm. There have been stronger cycles. There have been quieter ones. There have been mysterious radiation spikes whose origins are still debated. The sun's variability spans scales we are only beginning to fully appreciate. 3 gentle jokes later, and you might imagine historians and astrophysicists sitting at the same table arguing politely over coffee. Was 1770 worse? What about 774? Did cycle 19 set the real benchmark? The sun, meanwhile, blazes on, blissfully indifferent to the debate. In 2026, the difference is not that the sun has become unprecedentedly wild. It's that modern forecasting models slightly underestimated this cycle's vigor. That gap between prediction and reality is what captures attention. You breathe in slowly, feeling the quiet continuity of time. Generations before you watched unusual skies with awe and confusion. You watch with data, satellites, and live-streamed auroras. The tools have changed. The star has not. And as you drift toward sleep, consider this. The sun's present behavior will one day become another entry in the historical record. Future scientists may look back at 2026 and say, "Ah, yes, that was the cycle that ran a little hotter than expected." Just another chapter in a 4.6 billion year story. The past whispers context. The present hums with instruments. And the sun continues its long, restless dance. Sometimes quieter than predicted, sometimes louder, but never truly static. As historians leaf through centuries of sunspot sketches and isotope spikes, one particular phrase begins to circulate more often in 2026 conversations. Half cautious, half speculative. Grand minimum. You've already wandered through the Maunder minimum and the Dalton minimum, those prolonged lulls when sunspots nearly vanished and solar activity quieted for decades. So now, with cycle 25 behaving more energetically than predicted, you might assume talk of a minimum would fade away. And yet, paradoxically, it hasn't. Mainstream fact: solar cycles vary in strength, but there is currently no solid evidence that we are heading into an imminent grand minimum. In fact, cycle 25's above forecast activity suggests the opposite of a dramatic shutdown. Sunspot numbers have climbed robustly, and magnetic complexity has remained elevated. So why does the question linger? Because some early predictions, made before the cycle ramped up, suggested that solar activity might continue the declining trend seen from cycle 21 through cycle 24. A few researchers even proposed we might be entering a new Maunder-like period within a few decades. Those forecasts were based on weaker polar field strengths at the end of the previous cycle. But 2026 has complicated that narrative. The polar magnetic fields, while initially modest, have reversed amid stronger than expected surface activity. Sunspot counts have surpassed conservative projections. Flares and CMEs have been more frequent than anticipated. If this is the doorstep of a grand minimum, it's wearing surprisingly energetic shoes. Historians still argue whether grand minima begin abruptly after strong cycles or emerge gradually after a series of weakening ones. The historical record is incomplete. Telescopic observations only go back 4 centuries. Isotope proxies stretch further but lack fine detail. We don't yet have a clear, predictive fingerprint for how a grand minimum announces itself. You imagine the sun's dynamo as a vast, churning engine. Could it gradually wind down over several cycles? Possibly. Could it also surprise us with alternating strong and weak cycles before any long-term lull? Also possible. The dynamo is nonlinear, influenced by turbulent plasma flows that are extraordinarily difficult to simulate perfectly. In 2026, some researchers are revisiting dynamo models that allow for stochastic fluctuations, essentially random variations layered on top of the regular cycle. These models show that even during generally stable periods, occasional stronger or weaker cycles can occur without signaling a long-term trend. Cycle 25 may simply be one of those stronger deviations. A quirky tidbit for your drifting thoughts. During the Maunder minimum, so few sunspots were observed that some early astronomers speculated the sun might have permanently changed its nature. Imagine declaring, well, that's it. The sun is done with spots forever. A few decades later, they returned. The sun enjoys proving definitive statements premature. Back in 2026, measurements of open magnetic flux, sunspot area, flare frequency, and helioseismic flow patterns do not indicate a collapse of the solar dynamo. Quite the opposite, the dynamo appears vigorous, but that doesn't fully silence speculation. Historians still argue whether grand minima are triggered by subtle shifts in meridional flow speed or by fluctuations in magnetic flux transport between hemispheres. The current hemispheric asymmetry in the pole reversal adds nuance to that discussion. So could uneven hemispheres foreshadow instability decades down the line? Or is asymmetry simply a normal feature of active cycles? You stand beneath a steady afternoon sun, unaware of debates unfolding in academic journals. To you, it feels constant, and in many ways it is. Solar luminosity remains stable. Fusion continues serenely. But surface magnetism is where variability lives. 3 gentle jokes later, and you might imagine scientists peering at graphs saying, is this the beginning of a quiet era? While the sun responds with another enthusiastic flare, just to keep things interesting. There's also a broader perspective to consider. Even during grand minima, the sun does not turn off. It continues fusing hydrogen. It continues shining. The difference lies mainly in magnetic surface activity, sunspots, flares, uneven and associated space weather. A grand minimum would likely reduce auroral frequency and geomagnetic storms, not plunge Earth into darkness. In 2026, the immediate evidence points away from an imminent, prolonged lull, but the conversation persists because long-term forecasting remains uncertain. The solar dynamo operates on timescales we are only beginning to map comprehensively. 4 centuries of telescopic data is a blink in stellar time. Researchers are now integrating helioseismic flow measurements, polar field strength data, and sunspot migration patterns into more sophisticated predictive models. The unexpected strength of cycle 25 is forcing recalibration. Predictions for cycle 26 are being adjusted in light of new observations. You sense a quiet humility in this process. For decades, scientists have grown more confident in cycle forecasting. Yet 2026 serves as a reminder. The sun still holds surprises, not catastrophic ones, just enough to keep certainty at arm's length. Historians still argue whether humanity tends to overinterpret short-term variability as long-term destiny. A single strong cycle does not define a century. A quiet decade does not guarantee a grand minimum. Patterns require patience. As you drift toward the soft edge of evening, the sun dips lower on the horizon. Its face appears smooth and golden, hiding the tangled magnetism beneath. Whether future decades bring stronger cycles or quieter ones, the star will continue its patient fusion. For now, 2026 does not whisper minimum. It hums with magnetic energy. It flares with enthusiasm. It expands auroral ovals and nudges satellites. The question of a grand minimum remains open, not because evidence demands it today, but because the sun's long rhythms are still being deciphered. And you, small beneath this restless star, are living in a year that reminds scientists of something essential. Prediction is an evolving art when your subject is a 4.6 billion-year-old sphere of plasma with a flair for improvisation. As debates about grand minima ripple through research papers, you begin to notice something closer to home. Not in the sky, not in the sun's core, but in your pocket, your phone. Modern civilization hums on invisible threads, electromagnetic signals, satellite timing pulses, high-frequency radio links, undersea cables synchronized by atomic clocks that themselves rely on space-based calibration. The sun has always influenced Earth, but in 2026, the difference is how deeply you've wired your life into technologies that extend beyond the atmosphere. Mainstream fact: GPS satellites orbit at about 20,000 kilometers above Earth and transmit timing signals so precise that even nanosecond errors can affect positioning accuracy. During strong solar storms, increased ionospheric disturbances can delay or refract those signals, reducing GPS accuracy. This has been documented repeatedly during past solar maxima. In 2026, with more frequent geomagnetic disturbances than originally forecast for this phase of the cycle, GPS performance reports have shown intermittent regional degradations during peak storm intervals. Not total failure, not planes falling from the sky, but measurable accuracy drift, sometimes meters instead of centimeters for high-precision systems. You imagine a farmer using GPS-guided tractors for precision agriculture, a surveyor mapping land boundaries, a shipping company routing cargo. For most people, a few meters of error is harmless. For certain industries, it matters. Historians still argue whether society's increasing dependence on satellite navigation represents a quiet vulnerability. Before GPS, ships relied on sextants and radio beacons. Planes use ground-based navigation aids. Today, redundancy exists, but GPS has become foundational, and GPS is only one thread. High-frequency, HF, radio communication, still used for aviation over oceans and in remote regions, depends on predictable ionospheric reflection. Solar flares can cause sudden ionospheric disturbances, absorbing HF signals and creating radio blackouts on the sunlit side of Earth. In 2026, several strong flares have triggered brief but widespread HF disruptions, requiring rerouting or switching to backup communication systems. You picture a pilot cruising above the Arctic Circle. A flare erupts 8 minutes earlier on the sun. X-rays flood Earth's upper atmosphere, increasing ionization in the D layer. HF signals that would normally bounce between ionosphere and ground are absorbed instead. Controllers shift frequencies. Protocols activate. Calm adjustments. 3 gentle jokes later, and you might imagine the sun occasionally flicking the cosmic light switch just to see if humanity remembers its backup plans. Then there are satellites providing internet service. Thousands of them now orbit in low Earth orbit, forming constellations. Elevated atmospheric drag in 2026 has forced more frequent orbit-raising maneuvers. Each maneuver consumes fuel. Over time, fuel budgets shape mission lifetimes. Meanwhile, space tourism, still in its early chapters, must account for heightened radiation during active solar periods. Astronauts aboard the International Space Station already retreat to shielded areas during major solar particle events. In 2026, those precautionary steps have been exercised more often than early cycle forecasts suggested. Historians still argue whether humanity's technological expansion into space has outpaced public understanding of space weather risks. On the ground, solar storms feel abstract. In orbit, they are operational realities. You consider financial systems. High-frequency trading networks depend on precise timing. That timing often relies on GPS signals. If ionospheric disturbances introduce microsecond-level errors, which backup systems compensate, but complexity grows. Power grids, satellite networks, aviation routes, maritime navigation, emergency response coordination, all interconnected. None fragile in isolation, but collectively sensitive to electromagnetic variability. And here's the quiet irony of 2026. The sun is not unleashing record-breaking superstorms. It is simply exceeding modest forecasts. That slight excess matters because modern infrastructure operates with tight tolerances. A quirky tidbit for your drifting mind. In 1972, between the Apollo 16 and Apollo 17 missions, a massive solar particle event occurred that would likely have delivered a dangerous radiation dose to astronauts had they been en route to the moon at the time. The timing was fortunate. Space exploration, it turns out, occasionally benefits from good luck. Today, where mission planners use real-time solar monitoring to reduce reliance on luck, spacecraft can delay maneuvers. Astronaut EVAS can be postponed. Launch windows can be adjusted. In 2026, heightened vigilance has become routine. You sit comfortably indoors, scrolling, streaming, navigating. Each digital action subtly entwined with systems above the atmosphere. The sun's activity ripples through those systems, not catastrophically, but persistently. Historians still argue whether the 21st century will be remembered as the era when humanity fully integrated space weather forecasting into daily infrastructure management. In 2026, that integration is clearly underway. Forecast models update hourly, alerts distribute automatically, engineers respond in near real time, and yet prediction remains imperfect. The sudden flare without clear precursor, the CME that arrives slightly earlier than estimated, the solar wind stream that runs faster than expected. You feel a quiet respect growing. The sun does not need to rage to remind you of your dependence. A few extra G3 storms, a handful of strong flares, a thermosphere puffed just a bit more than planned. That's enough to test resilience. As evening settles, your devices continue functioning. Signals bounce, data flows, the grid hums, the magnetosphere shields. The fragility is not dramatic, it is conditional. Conditional on monitoring. Conditional on adaptation. Conditional on paying attention to a star 150 million kilometers away. And in 2026, that star is acting differently. Just differently enough to keep the guardians of your digital world awake a little later, watching solar dashboards glow softly in darkened control rooms. The sun blazes on, you scroll on, and between you stretches an invisible web of electromagnetic dependence, vibrating gently in response to a restless, improvising star. If Earth feels the sun's restlessness as a series of nudges, drag here, aurora there, then step just a little farther out, beyond the comforting cocoon of Earth's magnetic field, and those nudges become far more direct. You leave the planet now in your imagination, drifting past the thinning atmosphere, past the orbiting satellites making their careful adjustments, and into open space. Mainstream fact: Earth's magnetosphere shields the surface from most charged solar particles. Mars, by contrast, lacks a global magnetic field. It has patchy crustal magnetism, remnants of an ancient dynamo, but no planet-wide shield. The Moon has none at all. In 2026, as solar flares and coronal mass ejections cluster more energetically than forecast, radiation levels beyond Earth's protective bubble have become a sharper concern for mission planners. Imagine standing on the Moon. The sky is black even at noon. The sun blazes unfiltered. There is no thick atmosphere to absorb ultraviolet radiation. No magnetic field to deflect energetic particles. When a solar particle event erupts, streams of high-energy protons accelerated by flares or CME shock fronts, those particles can strike the lunar surface directly. Astronauts on future Artemis missions must take this seriously. Habitat designs include radiation-shielded compartments. Mission control monitors solar activity continuously. In 2026, with more frequent strong flares than predicted early in the cycle, simulation exercises have been updated to reflect shorter warning windows. Historians still argue whether early space programs underestimated solar radiation risks due to limited data. During the Apollo era, knowledge of solar particle event frequency was incomplete. That near miss in 1972 between lunar missions remains a sobering example. Today's planners have better forecasting tools, but forecasting is never perfect. Now drift farther still toward Mars. Mars's thin atmosphere provides some protection, but without a global magnetosphere, solar wind and CME impacts interact directly with the upper atmosphere. Over billions of years, this process likely contributed to atmospheric loss. NASA's MAVEN spacecraft has measured how solar storms enhance atmospheric escape rates. In 2026, several CME impacts at Mars have been recorded as particularly strong, compressing the Martian ionosphere and boosting atmospheric sputtering. Not catastrophic, not stripping the planet bare overnight, but measurable. You picture a robotic rover on the Martian surface. Above it, a solar storm rages. High-energy particles penetrate the thin air, increasing radiation levels at ground level. Instruments record the spike. Mission teams note the data. Future human explorers would need shielding, habitats buried under regolith perhaps, or reinforced modules designed to withstand extended particle events. 3 gentle jokes later, and you might imagine Mars squinting at the sun and saying, "You again?" Beyond Mars, spacecraft exploring deep space also feel the difference. The Parker Solar Probe, venturing closer to the sun than any spacecraft before it, has encountered increasingly turbulent magnetic structures during its 2026 perihelion passes. Data show intensified magnetic switchbacks and denser plasma structures linked to the active solar surface. Solar Orbiter, observing the sun's poles from an inclined orbit, has captured unprecedented views of polar magnetic field restructuring during the uneven reversal phase. Those polar measurements are especially valuable this year as scientists try to understand hemispheric asymmetry. Historians still argue whether humanity's push deeper into space will eventually require a dedicated space weather forecasting network distributed throughout the inner solar system. Earth-based monitoring provides advance warning, but once humans travel regularly to the Moon or Mars, localized measurements become essential. In 2026, agencies are refining radiation exposure models for crewed missions based on real-time solar activity. Even commercial spaceflight companies track solar indices before suborbital launches. Most flights remain short enough that risk is minimal, but awareness has grown. You float now between Earth and the Sun, aware of how thin your protections would be without atmosphere and magnetism. The solar wind streams past at hundreds of kilometers per second. Magnetic fields ripple. Occasional shock waves from CMEs propagate outward like invisible tsunamis. The sun's increased activity this year hasn't halted exploration, but it has sharpened caution. Spacecraft designers factor in radiation hardening. Mission timelines include contingency plans for solar storms. A quirky tidbit to drift with. During intense solar storms, astronauts in orbit sometimes report seeing bright flashes, even with their eyes closed, caused by energetic particles interacting with the retina. Space, it turns out, has its own light show. Back on Earth, you are shielded. On the Moon or Mars, you would not be so fortunate. And that difference reframes 2026's story. On Earth, heightened solar activity is mostly a technological management challenge. In deep space, it becomes a biological hazard. Historians still argue whether the timing of solar cycles will influence when humanity attempts long-duration missions to Mars. Ideally, missions launch near solar minimum to reduce radiation exposure from solar particle events. But solar minimum also allows more galactic cosmic rays through. There is no perfect window, only trade-offs. As you drift back toward Earth in your imagination, you appreciate the invisible cocoon that wraps your planet. The magnetosphere flexes and absorbs. The atmosphere thickens and protects. The sun in 2026 is energetic, magnetic, improvisational. For Earth, it is a manageable dance partner. For explorers beyond Earth's shield, it is a force requiring respect and preparation. You settle once more beneath a familiar sky, comforted by gravity and air. The same star that powers life here becomes a harsher companion in open space. And as humanity stretches its reach outward, the sun's changing moods matter more than ever. Not because it is out of control, but because we are venturing farther from the shelter that once made its variability almost invisible. In 2026, exploration and solar physics are intertwined. The better we understand our restless star, the safer our steps beyond Earth will be. Whenever the sun behaves even slightly outside expectations, another phenomenon flares up, on Earth this time. Theories. Some are careful and grounded in physics. Others wander. In 2026, as headlines mention stronger than forecast solar activity, unusual auroras, and asymmetric magnetic reversals, speculation spreads quickly online. You've seen it before. A vivid sky photo appears, and within hours, someone suggests planetary alignments are pulling on the sun, or that mysterious cosmic forces are awakening it. Mainstream fact: planetary gravitational forces on the sun are extremely small compared to the internal forces generated by plasma motion and magnetic fields. Jupiter, the most massive planet, it does exert a measurable gravitational tug, but it is tiny relative to the sun's own internal dynamics. There is no credible evidence that planetary alignments trigger solar flares or control solar cycles. And yet, the idea persists. You imagine the planets lined up neatly on one side of the sun, like children tugging at a giant parent's sleeve. It's a charming picture, but the sun outweighs all the planets combined by more than 99%. The gravitational dance is dominated by the sun, not choreographed by Mercury whispering suggestions. Historians still argue whether earlier civilizations, lacking knowledge of plasma physics, interpreted solar variability through mythological frameworks out of necessity rather than superstition. When you don't know about magnetohydrodynamics, a fiery dragon seems like a reasonable explanation for a red sky. In 2026, another fringe idea circulates: dark matter interactions influencing the solar core. Dark matter does exist. Its gravitational effects are well established in galaxies, but there is no compelling evidence that fluctuations in dark matter density near the sun drive short-term changes in solar activity. The sun's variability is overwhelmingly explained by its magnetic dynamo processes. Still, the concept captures imagination: invisible matter shaping a visible star. It sounds cinematic. Then there are whispers about the sun changing phase or entering some new, irreversible state. The language grows dramatic. The data, however, remain measured. Solar cycle 25 is stronger than early conservative predictions, but well within historical bounds. Solar cycle 19 in the 1950s was significantly more intense, and the Carrington event occurred during a robust cycle. 3 gentle jokes later, and you might picture the sun scrolling through social media and saying, "Oh, please, I've been doing this for billions of years." But it's worth acknowledging why speculation blooms. The sun feels personal. It dominates your sky. When it behaves differently, even slightly, it stirs a primal awareness. Unlike distant galaxies, this star sustains your life. Historians still argue whether public communication about solar science sometimes struggles to balance caution with reassurance. If scientists say, "the sun is more active than forecast," that can sound ominous. If they say, "everything is normal," that can sound dismissive. The truth often lives in the middle. The sun is dynamic, and our predictive models are improving but imperfect. In 2026, while mainstream solar physicists focus on refining dynamo simulations, incorporating updated helioseismic flow data, and analyzing magnetic flux transport patterns, the explanations remain rooted in plasma physics: differential rotation, turbulent convection, magnetic reconnection. Meanwhile, fringe forums discuss planetary torque cycles and exotic particles. The contrast is striking, a quirky tidbit for your drifting thoughts. In the late 19th century, some scientists proposed that sunspots might influence Earth's stock market cycles. Statistical correlations were claimed. Later analyses found no robust causal link. The sun, it turns out, is not secretly day trading. And yet curiosity is not the enemy. It's the beginning of inquiry. Even unconventional ideas can inspire useful questions, provided they are tested rigorously. Science thrives on skepticism, but also on evidence. In 2026, the evidence points toward a relatively strong, magnetically complex solar maximum unfolding slightly ahead of schedule. It does not point toward cosmic conspiracies or stellar metamorphosis. You stand beneath the night sky, perhaps still glowing faintly with auroral residue at the horizon. The sun is out of sight now, but its influence remains. There is something humbling in recognizing that a star can behave entirely within the laws of physics and still surprise you. You don't need exotic forces to explain unpredictability. Nonlinear systems like turbulent plasma dynamos naturally produce variation. Historians still argue whether humanity tends to fill gaps in understanding with narratives that feel emotionally satisfying rather than empirically grounded. The sun has inspired gods, myths, calendars, and cults. In the digital age, it inspires viral threads. But here, in the quiet of your own awareness, the story is simpler and perhaps more beautiful. A giant sphere of plasma, rotating, convecting, twisting magnetic fields through fluid motion, occasionally exceeding forecast strength because chaotic systems are inherently difficult to predict precisely. No dragons required. As you exhale slowly, the speculative noise fades. What remains is the steady glow of evidence. Spacecraft data, neutrino counts, magnetograms, helioseismic oscillations. The sun is acting differently in 2026, not mysteriously, not supernaturally, but dynamically. And sometimes, the most astonishing explanation is the ordinary one. Physics doing exactly what physics does when billions of tons of ionized gas swirl inside a star. You feel a quiet comfort in that. The universe is strange enough without adding extra ingredients. And as the Earth turns, carrying you gently toward another sunrise, you know that the star waiting at the horizon needs no conspiracy to be magnificent. It is already complex beyond imagination. By now, in 2026, something subtle but significant has shifted, not in the sun alone, but in the way scientists model it. Forecast curves that once felt comfortably confident are being redrawn. Mainstream fact: solar cycle predictions are generated using a combination of precursor methods, like measuring polar magnetic field strength near solar minimum, and dynamo-based computer simulations that attempt to model plasma flow and magnetic flux transport inside the sun. These models have improved steadily over the past few decades, but they are not perfect. When Solar Cycle 25 began in 2019, the official consensus forecast suggested a relatively modest peak, comparable to the weaker Cycle 24. That forecast was grounded in measured polar field strengths and surface flux transport models. It wasn't guesswork, it was evidence-based. But as sunspot counts climbed faster than anticipated and flare frequency exceeded median projections, researchers began updating their models in real time. Once you imagine a supercomputer simulation of the sun, a glowing sphere divided into millions of grid cells, each calculating fluid motion, magnetic induction, turbulence. Equations of magneto-hydrodynamics churn forward in tiny time steps. For years, those simulations matched observed trends reasonably well. Now in 2026, discrepancies have appeared. Not catastrophic failures, just enough divergence to require recalibration. Historians still argue whether solar cycle forecasting will ever achieve the precision of terrestrial weather prediction. Weather models benefit from dense, direct measurements across the atmosphere. Solar models must infer interior flows indirectly through helioseismology and surface magnetograms. The sun's interior remains partially hidden, like an engine we can hear but not open. One area of focus this year is flux emergence rate, the speed at which magnetic flux tubes rise from the convection zone to the surface. If that ascent happens faster than expected in certain latitudes, sunspot formation can outpace forecasts. Helioseismic data suggesting altered meridional flow speeds may be part of that explanation. Another area under revision is hemispheric coupling. Earlier models assumed relatively tight synchronization between northern and southern hemispheres. The uneven magnetic reversal in 2026 suggests that hemispheres may evolve more independently than previously thought. That independence complicates cycle amplitude predictions. 3 gentle jokes later, and you might picture modelers muttering, "Okay, son, you win this round," while adjusting parameters in their code. But there's no defeat here, only refinement. Science advances precisely when predictions meet reality and adapt. Space weather forecasting, in particular, has grown more dynamic this year. Machine learning systems trained on historical flare data are being retrained with fresh 2026 observations. CME propagation models are being adjusted to account for slightly faster average transit speeds during clustered events. Historians still argue whether artificial intelligence will significantly outperform traditional physics-based models in predicting solar eruptions. Some believe pattern recognition in vast datasets will uncover precursors humans overlook. Others caution that without physical grounding, AI models risk overfitting past cycles. In 2026, hybrid approaches, combining physics equations with machine learning corrections, are gaining traction. Meanwhile, polar field strength measurements following the asymmetric reversal are being fed into early cycle 26 forecasts. It's too soon for certainty, but preliminary models suggest the next cycle may not be as weak as once assumed. You feel the quiet rhythm of iteration. Observe, predict, compare, adjust, repeat. It mirrors the sun's own cycles in a way. A quirky tidbit for your drifting thoughts. Early solar cycle predictions in the 20th century sometimes relied on statistical correlations with geomagnetic indices alone, without detailed dynamo modeling. Forecasting was as much art as science. Today's models are far more sophisticated, but humility remains part of the equation. In 2026, the key lesson is not that scientists were wrong, and it's that uncertainty bands exist for a reason. Solar Cycle 25 has landed toward the upper end of its predicted range, perhaps even nudging beyond it in certain metrics. That nudge is enough to spark revisions, conferences, late-night coding sessions. You imagine researchers overlaying historical cycles on transparent sheets, comparing shapes. Cycle 19 towers high. Cycle 24 dips low. Cycle 25 rises confidently somewhere in between, but with sharper flare clusters than anticipated. Historians still argue whether long-term solar variability follows quasi-periodic rhythms or is fundamentally chaotic beyond a few cycles. If chaotic elements dominate, then precise amplitude forecasts decades in advance may remain elusive. If hidden periodicities exist, deeper data mining might reveal them. Either way, 2026 becomes a case study, a reminder that the sun does not owe consistency to human expectation. And yet the models are improving. Each unexpected surge feeds new data into simulations. Each asymmetric reversal refines assumptions about hemispheric coupling. Each flare without clear precursor sharpens machine learning training sets. You stand beneath a bright afternoon sun, unaware of the terabytes of data streaming from orbiting observatories into research centers worldwide. But that data is being digested, analyzed, incorporated. The sun's behavior this year has not shattered understanding. It has stretched it, and that stretching is healthy. As you exhale slowly, imagine the global network of solar observatories, spacecraft like Parker Solar Probe, Solar Orbiter, SDO, forming a distributed sensor array around a star that once seemed untouchable. Humanity is not merely watching the sun now. It is modeling it, simulating it, iterating on it in digital form. The forecast will grow sharper, the uncertainty margins narrower, but even then, a degree of unpredictability will remain. Because turbulence by its nature resists perfect prediction, and perhaps that is part of the beauty. The sun in 2026 has reminded scientists of both their progress and their limits. Models are rewritten, parameters adjusted, confidence recalibrated, not diminished but matured. As evening approaches and sunlight softens into gold, you realize something quietly reassuring. When the sun acts differently, science does not panic. It updates. And that process, steady, methodical, self-correcting, is as reliable as fusion in the core. And now you arrive at a quieter realization. After the flares and the CMEs, the asymmetric pole reversals and the humming transformers, the drifting auroras and the rewritten models, after all of it, you are still here. The sun rises, the sun sets. In 2026, it has behaved more energetically than forecast. Sunspot counts climbed higher than early predictions suggested. Flares erupted with less warning. Coronal mass ejections clustered and traveled quickly. The solar wind blew in brisker streams. Satellites adjusted. Power grids monitored. Scientists recalibrated, but life on Earth continued. Mainstream fact, the sun has increased and decreased in magnetic activity for billions of years. Geological and isotopic records show variability long before humans existed. Yet through those fluctuations, life evolved, oceans formed, forests grew. The sun's variability is real, but it operates within bounds that have sustained biology for eons. You stand beneath that same star tonight. It looks unchanged to your eyes, steady, golden, almost serene. And in total brightness, it is remarkably stable. The variations you've traced through this journey are mostly magnetic, mostly invisible, mostly detectable only through instruments and analysis. Historians still argue whether humanity's awareness of solar variability changes our psychological relationship with the sky. Once the sun was a deity, then it became a furnace. Now it is a dynamic plasma laboratory whose moods are charted in real time. Knowledge replaces fear, but perhaps also adds a new kind of respect. You think back to the monks sketching red skies, the astronomers tracing sunspots by hand, whilst the telegraph operators shocked by geomagnetic currents, the early space engineers surprised by atmospheric drag. Each generation encountered a sun that behaved differently compared to expectations of the time. And each time, understanding grew. In 2026, the difference is subtle but important. We can detect deviations quickly. We can measure helioseismic flow speeds. We can count neutrinos. We can watch magnetic field lines twist in ultraviolet light. We can simulate plasma dynamics on supercomputers. The sun is not becoming unstable. It is reminding us that even well-studied systems retain complexity. 3 gentle jokes later, and you might imagine the sun smiling, if a star could smile, at humanity's spreadsheets and forecasts. You've learned a great deal, it might say. Kane, but don't get too comfortable. Historians still argue whether solar variability will ever surprise us with an event truly beyond modern precedent. The Carrington event remains the benchmark for extreme geomagnetic storms in recorded history. Could something larger occur? Statistically, yes, though rarely. That possibility is not new to 2026. What is new is the density of infrastructure now orbiting Earth and stretching across its surface. And yet, resilience has grown alongside vulnerability. Forecasting centers operate around the clock. Spacecraft are hardened. Grids are monitored. Mission planners adapt schedules around solar cycles. Humanity has woven awareness of space weather into its technological fabric. You inhale slowly, the air feels ordinary. The sky above is dark now, perhaps scattered with stars. Somewhere on the other side of the planet, dawn approaches. The sun continues its fusion, converting hydrogen into helium at a steady, unhurried pace. Deep inside, neutrinos stream outward as they always have. In the convection zone, plasma churns. At the surface, magnetic fields knot and unknot. The poles complete their uneven reversal. The solar wind breathes into space. Acting differently does not mean acting dangerously. It means acting dynamically. And perhaps that is the truest lesson of 2026. You are orbiting a star that is alive with motion, turbulent, magnetic, improvisational. It does not tick like a metronome. It pulses, sometimes stronger than predicted, sometimes quieter, always governed by physics, yet rich with complexity. Historians still argue about past minima and maxima. Scientists debate dynamo models and flux transport speeds. Engineers refine systems to tolerate variability. Meanwhile, the sun simply continues being what it has always been, a vast sphere of plasma obeying the laws of electromagnetism and gravity. As your thoughts begin to slow, you feel less like a passive observer and more like a participant in a cosmic dance. Every sunrise is a reminder of fusion in action. Every aurora, a reminder of magnetic connection. Every satellite signal, a quiet handshake with space. The sun in 2026 is not a harbinger of doom. It is a teacher of humility, a reminder that prediction is a process, not a promise. And as you settle deeper into stillness, you realize something gently reassuring. Even when the sun surprises us, it does so within a universe governed by knowable laws. The mystery is not chaos. It is complexity. The star that warmed the first oceans still warms you now. Its moods ripple outward, occasionally nudging your technology, occasionally dazzling your skies, but it remains your star, steady in brightness, dynamic in magnetism, patient in fusion, and tomorrow it will rise again, perhaps with another unexpected flare, perhaps quietly, continuing the long, radiant story you are fortunate enough to witness. Let your thoughts drift like solar wind now, gentle and unhurried. The sun is vast. You are safe beneath your atmosphere and magnetic shield. The models will update, the data will refine, the star will continue, and you can rest knowing that even a restless sun still shines with dependable warmth. Word count 1,110. Now let your breathing slow. Imagine the sunlight softening into dusk. Oh, the magnetic storm settling into quiet ripples far above. The instruments keep watching, but you don't need to. The fusion at the core remains steady, ancient, untroubled. Feel the scale of it all gently shrink back down to something comforting. A warm glow through a window, a sunrise on the horizon, a familiar brightness on your skin. The sun may twist and flare and surprise the scientists who study it, but to you tonight it is simply a distant hearth in the sky. The plasma churns, the neutrinos stream. The magnetic fields slowly unwind and reweave themselves in patterns too vast to hold in waking thought. And that is all right. You don't need to calculate solar flux or trace field lines to rest beneath them. Above you, the heliosphere hums softly, one a great protective bubble breathing in rhythm with a star that has practiced this dance for billions of years. The forecast will come and go. The cycles will rise and fall. But right now there is only quiet. Only the steady turning of Earth. Only the distant glow of fusion. Only the calm certainty that morning will return.